Всем доброе утро.
Доброе утро.
Доброе утро.
Okay, I think we can start. We had a great day today. Hello, everyone. We had a very great day yesterday, and now we start the second day of our conference, Shabat 70. And the first speaker is Leonid Chekhov.
Okay, so it is my definite pleasure to give a talk on this nice conference devoted to the jubilee of my friend George Shabat. And I wish, from the very beginning, I wish Yura a good health and creativity for many, many years to come. And actually, what I'm about to talk about in this not very long talk is it's not quite so much related to the stuff that Yura was doing, but in fact, the essence or the spirit of it's close, because what we usually try to do is to reduce first something hard things to simpler things, like we, or not we, but of course Yura and collaborators, they use this reduction, this transition between, say, difficult stuff related to belly functions to stuff that can be explained even to children, like Grothendieck descent and found. And actually, the idea of my activity that is presented here, so it's based on these three papers that I indicated, mostly joined with Misha Shapiro, is to reduce some important and relatively difficult things to easier parts, to easier things that, again, that we know that if we have some involved algebras, like the algebras that we have in integrable systems, we are always searching for some simpler representation of these algebras. And so happened in the last 20 years that important and attainable description that we can do is somehow related to this stuff that we call now cluster algebras. But on the other hand, we can always think about elements of these algebras as just Darboux coordinates, so, or canonical coordinates. And clusterization pertains to just transformations between different maps on the same manifold. And these maps happen to be always irrational maps in this story. I want to present how it's all developed, starting with a special construction that we call the groupoid of upper triangular matrices, and which, as we learned in the last 20 years, is closely related to integrable systems, namely to reflection equations. And then I want to show how these groupoid and these reflection equations can be embedded into planar networks and algebras that we call algebras of quantum transport matrices. So they, as we'll see, they satisfy the standard Lipposon algebras that can be described in our matrix way. So one of motivations of this activity actually has also a long story, and it will be basically main object of my talk today. So we consider the following structure. Consider the subspace of unipotent upper triangular matrices in some basis of linear space. And well, we can think about elements of this subspace or as this space itself as in bilinear forms in the corresponding linear space. And as bilinear forms under change of the basis, they transform not in they transform as in this strange form as A comes to be A B transposed, not inverse. So it's not adjoint action, it's action on the space of the forms. And we can consider the space of morphisms, namely the pairs of DNA, such that both B and A are matrices. A is unipotent, B is whatever it is, some matrix from GL Vn. And the condition of this morphism is that the action of this matrix B itself is unipotent. So apparently it imposes some conditions on this matrix B, and these conditions are highly nonlinear, and basically we cannot resolve them into full extent even in the simpler cases of n equals 3 or 4. But what is, however, known is that this action and these morphisms, they enjoy a standard symplectic structure from the works of Karashev and Weinstein. It's somewhere 80s of previous century. And this structure is compatible with the groupoid composition law. Of course, I skip most details in this talk, but what is actually what is nice in this structure and what is remarkable is that the corresponding structure also, which can be easily, relatively easily quantized, actually produces upon identical mapping when we collapse this algebra to the algebra of elements of the matrix A. This element satisfies this famous algebra, which is either classically or quantum algebra, which is actually coincide with the algebra of geodesic functions on Riemann surfaces of some genus. So the same algebras appeared in many more ways and in many more papers. From the physical side, it was by Jeanette Nelson and Tullio Reggi. And from mathematical physics side, they were in Monica Ugalia paper and papers of Monica and Boris Dubrovin. So just to mention that indeed these algebras are famous in a sense, and they definitely worth studying. And again, if I don't have time to make excursion into geometry, but to mention, I have to mention it, that indeed these algebras, they correspond to algebra subs of intersecting geodesic functions on the Riemann surface. For instance, if I have two geodesics with a single intersection, then they satisfy these classical relations. And if I consider the corresponding quantum objects, they satisfy the corresponding quantum relation, and so and so and so. So, and then even if you have a look at paper of Volodymyr and myself, we develop the correspondence between elements A and the corresponding geodesics on the Riemann surface of genus that is approximately half the size of these matrices. And here we have, so we actually, to quantize, we just associate, we just consider all elements of this matrix A to be upper, so the elements above the diagonal are just Hermitian operators related to quantum geodesic functions. On the diagonal, by some reason, we have to put this, instead of units, we have these Qs, well, but this is common in this quantization business. So the operators above the diagonal are self-adjoint, and then we can actually represent the algebras from the previous page in some concise way as these algebras of reflection equation, quantum reflection equation, where R is a trigonometric, what is called trigonometric R matrix. And there was, however, some subtlety in this business for years, and it was related, oops. It was related to the following observation, that if we consider the dimensions of the corresponding algebras, so then we have that the genus is as I say, about approximately half of the size of this press not the right button. So here is the dimension, and we have not just a smooth Riemann surface, but surface with either one or two holes. And then we observe the dimensions of the corresponding spaces. On one side, we have dimension of the corresponding touch mirror space. On the other side, we have just the dimension of the corresponding space of upper triangular matrices. One dimension grows linearly with the size of this matrix, another grows quadratically, so apparently they start to diverge. They match for the basically first two values of n, and even for the third value, they almost match because the Poisson dimension remains the same. But then they start diverge wildly, and this means that in geometry, the corresponding geodesic functions are just Poisson leaves of lower dimension inside the corresponding manifold. For the corresponding geometrical leaves, we again from since last century we have description in terms of triangulations of surfaces. So we have canonical coordinates related to triangulations, so namely the shear coordinates, and we can express the corresponding elements, the corresponding geodesic functions as just Laurent polynomials of those coordinates, and we can construct the corresponding algebras, check that the corresponding equations are satisfied. But we didn't have so far the corresponding simple description for general Poisson leaves for higher n is. This was the first motivation of this activity, and second motivation was related to actually braid group transformations, which in geometrical language are related just to the corresponding twists along the corresponding geodesics on the Riemann surface. So we have two questions related to this structure. First, to find a cluster variable realization of a general symplectic leaf of this unipotent matrices A such that the corresponding the corresponding object satisfies the quantum reflection equation from the previous slide. And second, to find the cluster mutation realization of the braid group transformations. And actually, it was, for me at least, the problem that was open for 20 years. And happily, it was resolved in our joint paper with Misha Shapiro, which was published in EMN, which was published this year. And solution turns out to be related to structures that are not quite geometrical. So now we leave the domain of geometry and switch to algebras. And let me consider the following structure. So we consider the directed planar networks. And here we have one example, the main example that I will use. It's what is called Goncharov or Goncharov chain, Borel subgroup of SL6. But again, as I promised, we must have some simple description. So we can just think about it as some directed planar network. So it has first here on this slide you see, so we have the directed network itself and we have a dual graph. So what we calculate, we consider passes from, say, sources in this network to sinks. So sources are apparently its incoming arrows, sinks are outgoing arrows, and the path is just any path that actually respects somehow the corresponding laws with these arrows. And in the dual network, in the dual graph, we have vertices that correspond to faces of the original graph, of the original network, and faces actually contain the corresponding variables that we associate with classical or quantum cluster variables. And you see, there are some rules how we can draw these arrows in the dual graph. And these arrows actually indicate the corresponding commutation relations between the variables that are joined by these arrows. And you see that these commutation relations are homogeneous. So if we consider canonical coordinates here are just logarithms of these z variables. And to each path, we associate what we call a quantum weight, namely because it's planar, so we have a good notion of right and left in this picture. So we just take the product of all variables that are in all cells to the whatever, to the right of the corresponding path. So for instance, here I just take all variables from all this part of this graph. And we have the while ordering. So if we want to define it in a quantum way, and then, so for each path, we define the corresponding weight. And when I consider the matrix that we call the transport elements or transport matrices, elements of transport matrices, Mij, I are enumerate sources and j sinks, then we just take the sum over all paths in this picture. If we have some loops, so we also may allow to have some loops in this picture, then we also have to introduce this factor related to self-intersections of the corresponding paths. So you see that it's very much a general structure. And it can be defined for any planar networks with or without cycles. What is quite remarkable is that whatever this planar network is, the corresponding elements of these transport matrices satisfy closed algebras, classical or quantum. So quantum version was derived in, again, our paper with Misha Shapiro, and but classical semi-classical version was in still it's almost 13 years old. So it was in papers of 2 Mishas and 1 Alec in 2009. But anyway, you see that we indeed can define. So this now, this arrow, sorry, in this picture, these arrows just indicate the paths, the elements of transport matrix, not commutation relations. So they just indicate the paths in the corresponding planar network. Okay, so far so good. And again, so this is very general. We don't even impose conditions that this planar network has no cycles. It may have cycles. The only condition that we impose is that it's indeed a planar. So if I come back to this picture of the triangle of Fock and Goncharov coordinates, then we observe that the corresponding matrices, so let me scroll up to this picture. So you see that we have one side with sources and two sides with sinks. And so the corresponding transport matrix is of size n times 2n. And we can actually consider two blocks of size n by n, so m1 and m2, and consider what are relations, what are quantum of semi-classical relations between these two n by n matrices. And what we observe is quite remarkable, that indeed the corresponding algebras can be written in R matrix form. So here we have this structure, for instance, for this, each of these metrics with itself, it satisfies more or less a standard Lie-Poisson relations, this one. But between these two matrices, we have some interesting relation. It's just one R matrix. where R matrix is here presented, so it's quantum, usually it's called in integrable systems, quantum trigonometric R matrix. Of course, it satisfies Yang-Baxter equation and everything. And now the last possibly statement that I will be able to present is that now if we just take these two matrices and multiply them here, consider this combination. And in quantum keys, it also implies that in this product satisfies corresponding ordering of operators, natural ordering. Then this matrix A enjoys the reflection equation. So indeed, the elements of this matrix satisfy the quantum algebra that was presented at the beginning of this talk. And therefore, if I identify the elements of this network, vertices of this dual graph with the canonical coordinates, these are canonical coordinates that coordinatize the corresponding place of unipotent quantum R matrices. And so we have, therefore, the Darboux coordinates for a general leaf of the Poisson groupoid of upper triangular matrices. And all elements of these matrices are Laurent polynomials of, so this is just what I denoted that alpha capital in the first part of the talk. So either Z alpha or Z alpha in inverse powers. And therefore we can actually find out the canonical coordinate representation of the corresponding reflection equation algebras. So in the last 2 minutes, I just mentioned that, again, I skip some technical details that are irrelevant. So actually, when we consider the corresponding quiver that now corresponds to A, it becomes, by some reason, it becomes now non-planar. As you see from here, there is an example for n equal 5. But these quivers enjoy again nice properties of symmetries. For instance, we can perform a series of mutations. Again, I will not describe how it works. You can find it in any standard text on cluster algebras, but it's really some very algorithmical and very simple transformations, elementary. And we can just find these sequences of these mutations such that the resulting quiver is isomorphic to the starting one. This means that we have the corresponding transformation on the corresponding mapping class group transformation in the space of variables, or modular transformation if these quivers coincide. And again, let me scroll to this picture so you can probably hardly recognize the previous triangle here, but it's just 2 copies of it. So one copy is here and another copy is joined, but with inverting the orientation from the lower side. And then if we just perform mutations, so starting at this vertex and going up to this vertex, to this red vertex, and then going down back to the original one, we obtain the quiver that has the same structure. So indeed, we solve both problems. So we have found the corresponding description of corresponding canonical coordinate description of the corresponding elements of unipotent algebras. And we also found the sequences of mutations that actually produce the break group transformation. So this is the end. I just want to mention some perspectives. And the first one is straightforward, and it relates to finding the cluster realization of the not just A by full system of being a morphisms. And it is actually done, and it is a forthcoming paper also with Misha Shapira. And moreover, as a byproduct, I just mentioned that we obtain a cluster representation or realization of closed Riemann surface or Teichmüller spaces of closed Riemann surfaces without holes. It was quite an unexpected and amazing continuation of this activity, but it's still in progress, so I don't have time to describe this part. But also I want to attract your attention that this all can be developed into many more directions. Of course, first and obvious is to consider representations of the corresponding quantum algebras and to find out what they correspond to, and to find out relations to invariants of knot and links, A polynomials, and possible topological recursion relations. But this is all, well, some program of activity for probably many years to come. And today I just want to conclude. Well, happy birthday, many happy returns. And again, Yura, have a long, very long and very productive life ahead. Thank you.
Thank you very much, Leonid. Very fascinating talk, topic. Maybe someone has some short question.
Oh, perhaps I have a stupid question. Can these results be developed in terms of the universal Teichmüller spaces and universal and infinite, infinite upper triangle matrices and so on?
Well, good question to which I don't have an answer. No, the answer is probably no, because it's all very new. So it just, again, it's one side that we were not able to touch in any case. But no, I agree, it's important question. But, and again, I hope that actually somehow, yes, this can be lifted to this universal Teichmüller spaces, because what is actually we have here is that, of course, it's very much specific to the size to some extent. It's on one hand, but on the other hand, the corresponding theorems about these algebras, they do not depend, say, for instance, on the size of the number of sources and things in the corresponding planar network. They are very much general. So we don't have any condition, for instance, what is the number of things or what is the number of sources, and even if they can be mixed on the boundary, so they can be interlaced. So I think there is a room for a description of the universal Tashmiel space here.
Thank you very much. Let's thank our speaker again. I invite our next speaker, Sergei Ilyashenko.
Greetings to everybody. My congratulations to Yulij Shabat. Many happy returns of the day. Let me start sharing my screen. I slightly changed the title of the talk. It is now Simultaneous Uniformization and Persistence Problems for Analytic Foliations, a lifelong project. Let me make the full screen. So the talk will deal with two major problems. One problem is about simultaneous uniformization. Given an analytic family of Riemann surfaces, does there exist a uniformization of these surfaces that depends analytically on the parameter of the family? What does it mean? When we have one Riemann surface, the uniformization is a classical problem, a classical result. And everybody knows what it is. A family of Riemann surfaces may be, say, a family of algebraic curves like level curves of a polynomial of two variables. Level curves corresponding to different values of the polynomials are not conformally equivalent. Yet we want to uniformize them simultaneously, that is, to find a uniformization function on the universal cover that will depend analytically on the value of the polynomial. Is it possible or not? This is the first problem. The second problem is a persistence problem. It is related to complex differential equations. Given an analytic family of differential equations, do the geometric features of the phase portrait persist when the parameter changes? For instance, let me say some elementary things. A phase curve of a complex differential equation is a Riemann surfaces, a one-dimensional complex manifold. So its topology may be depending on the initial condition. Some Riemann surfaces may be simply connected. Some Riemann surfaces may be not. A complex limit cycle defined by Petrovsky and Landis in 50s is simply a free homotopy class of loops of the Riemann surface, which is the phase curve. Weierstrass preparation theorem implies that when you slightly change the parameter, the complex limit cycle will never vanish. It may be split in several cycles, but never disappear completely locally. And this is in drastic difference with real limit cycles that may disappear when we change the parameters. So locally, the complex limit cycle does not vanish. What happens globally? You take an arbitrary curve in the parameter space, you follow for a while this limit cycle along this curve, may it happen that before you come to the end, the cycle will vanish. It may happen, but the more realistic question is, can you slightly change an arbitrary curve in such a way that the continuation of the limit cycle will become possible? This is the persistence problem. The persistence problem was stated by Petrovsky and Landis in 50s, and they made an attempt to give a positive solution. In the beginning of 60s, I found a mistake in their proof, and since then, this persistence problem became one of my targets. Problems 1 and 2, though they look quite different, are closely related to each other, as explained below. So the first figure is an illustration to the uniformization, just to recall everybody that I begin with the well-known things. On the left, a Riemann surface of a finite type, finite genus, and finite number of punctures is drawn. Then S hat is its universal cover, and the vertical arrow shows the uniformization map, the map to the unit disk. The naive concept of simultaneous uniformization might be the following. We take an analytic family of Riemann surfaces. It is plotted here. Do you see my mouse?
Yes.
Mm-hmm. So it is plotted here. A family of Riemann surfaces is just a total space and a map of the total space to a base. Let us think for simplicity that the base is always a disk B, and therefore the total space is two-dimensional. We have a holomorphic map of the total space to B, and the fibers of this map are Riemann surfaces in general of different complex type with different complex structures. The question is it possible to generalize the previous picture? That is to take a Cartesian product of a disk to B. It is plotted here. And to have a uniformizing map phi, which respects the fibers, and on any fiber is just the uniformization. This naive approach is hopeless. Such a uniformization, such a simultaneous uniformization, phi is holomorphic, exists only if all the fibers of the family, all the Riemann surfaces here, are conformally equivalent. So this attempt to define simultaneous uniformization is unlucky. Let us give a formal definition. Instead of the family of disks delta from the previous picture, we have so-called canonical skew cylinder. It is an open set embedded in the Cartesian product of the Riemann sphere to the base B with the natural projection P0. And any fiber of the canonical skew cylinder is a topological disk, but this disk may depend on the base point. the base B is still the disk. We have a family of Riemann surfaces. And for this family of Riemann surfaces, the simultaneous uniformization map phi is a holomorphic map that commutes with the projection. So phi p is simply p0. And it is a fiber-wise map. And on any fiber, phi is the universal cover map. This is the formal definition of the simultaneous uniformization. On the next picture, it is written down. So I repeat, a canonical skew cylinder is a triple, M0 embedded in the Cartesian product of the Riemann sphere to the base, with a natural projection on the base. The fibers are topological disks. And for a family of analytic curves, which is the triple total space projection and base, projection to the base, let this triple be a family of analytic curves. A map phi of M0 to the total space of the family is a simultaneous uniformization of this family, provided that the uniformization commutes with the projections pi times phi is pi0, and the map phi on any fiber of the canonical skew cylinder to the fiber of the curve of the family is the universal cover map. So this is the definition of the simultaneous uniformization. Now the first problem is rigorously stated. Given an analytic family, say one parameter family of Riemann surfaces, is the simultaneous uniformization possible? So this problem is partly solved, and I will tell you about partial results. The first result is classical. Simultaneous uniformization exists if all fibers of the family are algebraic curves, that is, Riemann surfaces of finite type, finite genus, finite number of punctures. They are homeomorphic to each other, and the base B is simply connected. So I said that the base B is one-dimensional, but not necessarily a one-dimensional disk. It may be, say, an annulus or something more complicated. This theorem is due to Burrs and Griffiths. The very term simultaneous uniformization is borrowed from Burrs. And this is a classical result that crowns Burrs' theory of Teichmüller spaces. A rather a stronger version of this result holds. So this is the first powerful positive result. B is simply connected. All the fibers are topologically equivalent. That is, the family is topologically trivial, and the simultaneous uniformization exists. The next result is due to our birthday hero, Yuri, and to myself. And this theorem is applicable to the case when the family to be uniformized consists of algebraic curves, but is topologically non-trivial. So the explicit formulation is the following. Simultaneous uniformization exists if the base is of dimension 1 and simply connected. All the fibers of the family, except for one, denoted by S0, are homeomorphic to each other. And the fiber S0 has but one simple crossing. In this case, the family is topologically non-trivial, even over the punctured disk with the 0 point deleted. And the problem becomes much more difficult than in the Burse-Griffiths case. Now, I will pass to the second part. What is the relation to differential equations? If we consider level curves of a polynomial, we can look at them as the phase curves of a Hamiltonian equation. So we take a Hamiltonian function, we write the Hamiltonian system, and the phase curves are the level curves of the map H of C2 to C. And the question is when the simultaneous uniformization is possible. The picture shows this map. C square is to the right, C square is to the left, C is to the right. One should write H instead of F over the arrow. The fibers are Riemann surfaces, and there are three versions of bases of the family. The first version is a topological disk consisting of non-critical values of H. For this disk, the answer is yes by the Burse-Griffiths theorem. The second version is a disk centered at a critical value in assumption that H has only Morse critical points. Then the answer is yes. And if the base is taken to be the whole of C, the problem is widely open. The answer is not yet obtained, and we really do not know whether the uniformization exists or not. Now, when we pass to differential equations that are non-Hamiltonian, to the left, I wrote a part of the phase portrait on the real plane, a limit cycle and a spirals winding to it. And when we consider the uniformization, we consider the set of universal covers over the fibers. So the base is the cross section, and one and the same fiber is repeated infinitely many times according to the base points on the cross section at which the phase curve crosses this section. The covering manifold over a family of phase curves is the union of the universal covers over these curves with the base point on some cross section. This cross section is considered as the base of the family, and the complex structure of this covering manifold, it is shown in the right part of the picture, is natural. A theorem due to Sherbakov and myself states that a space of universal covers over phase curves of a polynomial vector field in Cn with the Stein base, for instance, with the disk as a base, is a Stein manifold itself. So we come here to the theory of Stein manifolds, and there is a non-trivial reduction. Together with the theory of Stein manifolds and Köbe distortion theorem, the previous result implies the following reduction. If any holomorphic family of algebraic curves is uniformizable, then any holomorphic family of analytic curves with the Stein total space is also uniformizable. Now we come to the most dramatic point of the whole story. In 1999, Lutsuk discovered that there exists a non-uniformizable holomorphic family of analytic curves with the Stein total space. As a corollary, this implies, together with the previous theorem, that there exists a non-uniformizable holomorphic family of algebraic curves. This is a purely existential result. I have no idea how to construct a non-uniformizable family of algebraic curves. And a natural question arises, where is a boundary between uniformizable and non-uniformizable families of algebraic curves? Now I want to say a few words about the relation between the persistence and the uniformization. I told that the two problems about persistence and simultaneous uniformization are closely related. Now the corresponding theorem comes. Simultaneous uniformization, with some extra requirements that I skip for brevity, of the family of phase curve of some class of differential equations, implies persistence of limit cycle and Poincaré maps, whatever it means, for the differential equations of this class. This is a theorem published in 2006. The picture here shows what does it mean non-persistence of the Poincaré map. First of all, the Poincaré map of the complex differential equation is the same as for a real differential equation. You simply take two cross sections, the left and the right, and you map the left cross section to the right one along the phase curves of the equation. And if it happens that there is a disk in the source cross section, and a topological disk in the target cross section, and the map of the first disk to the second one, the Poincaré map, exists, but cannot be analytically extended across any boundary point of the first disk, then we say that this is non-persistence of the Poincaré map. So intuitively, you may take a definition of the persistence of the Poincaré map as forbiddance of this picture. So if this picture never occurs, we say that in this class of differential equations, the Poincaré map is persistent. Once again, a counterexample comes. Bertrand de Rouen, in reply to my conjecture, proved with authors the following theorem. There exists a polynomial vector field in the complex plane with a Poincaré map defined on a disk that cannot be extended through any point of the boundary of this disk. The foliation in this example admits simultaneous uniformization, but extra requirements from the previous theorems, from the theorems of 2006, are violated. This is a highly non-typical differential equation, polynomial differential equation. So the problem remains, what happens for typical differential equations? So I end up with several conjectures. The first conjecture: generic foliation by level curves of polynomial in two variables admits simultaneous uniformization. For instance, if in the picture that showed an example of the level curves of a polynomial, if in this picture we take the whole C as the base, the conjecture is that the simultaneous uniformization does exist. Now, a stronger conjecture. Complex phase curves of a generic polynomial vector field in the complex plane admit simultaneous uniformization. A Glutzuk counterexample shows that this is wrong for the phase space of dimension 5, but dimension 2 might be narrow enough to imply the positive answer. Now, a third conjecture: complex limit cycles of a polynomial vector field of given degree in the complex plane, again in the complex plane, admit an analytic continuation along a generic curve in the parameter space. So, as I explained before, you take an arbitrary curve in the parameter space, try to extend the complex limit cycle along this curve. Either you succeed and this is the end of the story, or you fail, but the conjecture says that you can find an arbitrary closed curve in the parameter space such that the extension of the limit cycle over this curve will be possible. And the last conjecture is that the Poincare map for a generic polynomial vector field of given degree in the complex plane has the persistence property. So for generic polynomials, the Bertrand-Derwin and co-authors example is impossible. So these are the conjectures that I am very much interested in and that I want to advertise. And here I come to the last part. Best wishes to Yuri. Many happy and healthy years. You are involved in childish drawings, and your lifestyle is as happy as the childish life. And this is great. Continue in this way. Best greetings.
Thank you.
Thank you very much. Anyone has a question? Okay. Thank you very much. Let's thank again our speaker. I'm glad to present our next speaker, Sasha Molyakov.
So thank you very much for inviting me here today, and I'm going to tell you about the Poincare theory and my recent result on the endomorphisms of the group of multiplicative groups. So let us start with some classical notion of the tame symbol, which initially appeared in algebraic number theory, I believe. So let K be a field, and we use the standard notations for the rings of formal Taylor and Laurent series with coefficients in K. And these rings have a natural variation V, which is just the maximal power of T dividing the series. And we can define the tame symbol for Laurent series F and G as -1 to the power of the product of valuations times F to the power of V of G over G to the power of V of F. And this expression has variation 0. I mean, this expression. So it is a Taylor series with a non-zero zero term. And if we consider it moduli T and K of T, then we get an invertible element in the field, which is called the tame symbol of two Laurent series. In particular, when so this symbol is bilinear, skew symmetric, and satisfies so-called standard property, that is F of 1 minus F is 1, provided that both F and 1 minus F are invertible. K of T star. Yes, And when K is a finite field, then we have two Laurent series with coefficients in P. And it turns out that the chain symbol to the power of P minus 1 over 2 coincides with the usual Hilbert symbol. So this expression equals 1 if the connex fx squared plus gy squared equals z squared has a rational point over fp of t. So there exists a solution with at least one of the variables non-zero, and otherwise this symbol is minus 1. So this was a classical part, and now I'm going to explain how this chain symbol can be extended to the case when we are working over an arbitrary ring rather than over a field. For this purposes, we need the following notions. Let R be a Q algebra. We call Laurent series F topological nilpotent if the valuation of the nth power of f tends to infinity. So nth power of f tends to 0 theoretically, and it is not difficult to check that this condition is equivalent to the following. If we write f equals sum ai to the i's power, then all the non-positive coefficients should be important. Then recall the standard Taylor series for the exponential and logarithmic mappings, and we define the exponent of a topologically important Laurent series just by substituting it into this Taylor series expansion, and it is well defined. So we simplify this expression. There would be finitely many summands with each power ti, and the same definition, a similar definition for the logarithm. It is well defined when f minus 1 is a topological nilpotent. Now let us consider a ring, which is a ring R, which is a Q algebra. Then the Cantu-Carrère symbol, which is a bilinear skew-symmetric pairing on the groups of invertible Laurent series with coefficients in R, taking values in R star, is uniquely defined by its properties. So first of all, it is bilinear, or probably it will be better to say by multiplicative, because it is just a pairing of evident groups. It is skew-symmetric, and so that is the first property. The second one is that a constant C paired with a series F is just C to the power of the valuation of F. Also, the formal variable T paired with itself is -1. And the last property, and the most important one, the following: when f minus 1 is a topological nilpotent, then we have the following Steres formula: the symbol of f and g equals to the exponent of the residue of logarithm of f dg over g. It turns out that that such symbol also satisfies standard property. So f paired with 1 minus f is 1. And in the case when the base ring R is a field, it just coincides with the usual chain symbol. And now I'd like to say a couple of words of how this can be defined, not just in the case of Q algebra, but over Z. We have the following curious identity: the symbol of 1 minus a t to the nth power 1 minus b t to the nth power equals 1 minus b to the power of n over GCD of mn over a to the power of n over GCD of mn to the power of this greatest common divisor. Well, and so you see that here there is no integer numbers in the denominators like they are when we are, I mean, when we are working with logarithm and exponents, and we have to divide by integer numbers, and therefore we make this assumption on Q algebra. But here there is no such thing, and the fact is that any Laurent series can be written as a product of some constant and t to the kth power times the product of such multiplies 1 minus ai t to the I power, where I greater or equal some minus n, not equal to 0, so just excluding 0. And then using that this thing is bilinear, and this well, this relation works when n is greater than 0 and n is less than 0. And if the sign of m and n is the same, then the symbol is just 1. It does not matter. Okay, let's move to the next slide. Now I would like to formulate a kind of universal property for this Cantu-Carrère symbol, and yes, and to formulate the Cantu-Carrère theorem, which is a way to obtain this symbol from some general perspective. Let us fix once and for all some base ring R, and by a group functor we understand the functor from the category of algebras to the category of abelian groups. And now we can define the loop group of G given a group functor G else in the following way. So this LG applied to an arbitrary algebra A is just G applied to the ring of Laurent series with coefficients in A. Similarly, we define DG, which is G applied to the ring of Taylor series, and a little bit more sophisticated object D check G, which is the inverse limit of G applied to A of t modulo t to the nth power, taken for all n. And let us notice that there are some natural morphisms from DG to LG. So this morphism is just induced by the natural embedding of Taylor series into the ring of Laurent series. And also there is a morphism from DG to D check G, which is induced by the system of projections from Taylor series to A of t modulo t to the nth power. And they give us an anti-diagonal morphism I minus j from dg to the direct sum of LG and d check g, and finally we can define L check g as this direct sum factored by the anti-diagonal image of dg. Also, so you although Taylor series, of course, can be presented as an inverse limit A of t modulo t to the nth power, yes, but it does not imply that dg necessarily coincides with d check. This dg necessarily coincides with d check g because the group of functor G is not assumed to commute with inverse limits, but if G so So if G is presented by an affine group scheme, then actually does commute with inverse limits, and in this case, dg just equals to the check G, and the corollary LG coincides with the L check G. So the situation is somewhat simpler. Now let us describe the above constructions for the case of multiplicative group in more detail. We use here some subscripts like ls, dg, lt, just to make some difference of different formal variables, not to confuse them. Well, LGM is just the group of invertible elements in the ring of Laurent series. LT, LS, GM are invertible double Laurent series. DT, LS, GM are Laurent series with coefficients in the ring of Taylor series, and DT, check T, LS, GM are Taylor series with coefficients in the ring of Laurent series, and this sophisticated group is LT, LS, GM. It is the sum of the two things factored by the third one. And let us notice that I claim that there is an interesting element actually sitting in this strange group. It is S minus T. And the reason for that is that S minus T is invertible in both direct summands and the numerator, but the reasons for that are different. Actually, let me write this down. S minus T inverse is S inverse 1 minus T over S inverse, and that is S inverse times sum of T over S to the I power, but also S minus T inverse is minus T inverse 1 minus S over T inverse, and that is minus T inverse the sum of S over T to the I power, and this element belongs to A of S of T, of the Taylor series of T, and that is the Laurent series of S with coefficients in Laurent series of T. So the difference for this element to be invertible in these rings are different, and you can notice that neither of these elements belongs to the denominator A of T of S. Therefore, it is something non-trivial, and thus we define the canonical element Xi, which is S minus T inverse, and that is an element of L check LS GM. Now consider a group functor G and an arbitrary morphism tau of group functors from LGM to G. Then just applying L check to the both sides, we get a morphism L check tau from L check LGM to L check G, and applying it to the base ring R, we get this morphism as it is written here. Now we are ready to define the main object for us, which is the Cantu-Carrera map from home LGM G to L check G of R, and it is defined in the following way. We just take this L check tau and compute it on the canonical element Xi, and to get an element in L check G of R. And now we can formulate the main result. in this theory by Cantu-Carrère. Let G be a group functor represented by a smooth separated commutative group scheme of finite type over a Noetherian ring R. Then the Cantu-Carrère map is an isomorphism from Hom LGM-G to maps isomorphically to L check G R. And as a corollary of this result, we see that there is a canonically defined non-degenerate pairing from LGM times HMG to G. And the simplest example of this, when G is just J, it is represented by an affine group scheme. Therefore, as I said, L check J just coincides with LJ, and we have the pairing between the multiplicative group of Laurent series and additive group of Laurent series with values in the ring, and it has the following simple form: GF maps to the residue of F dg over G. So a more interesting example is when G equals GM, then we just get the Cantu-Carrère pairing that we have defined before. And now I would like to formulate my written result about the endomorphism of the loop group of the multiplicative group. And it is, in some sense, it is an analog of the Cantu-Carrère theorem for the non-representable functor LGM. So let R be a pure algebra. Then it turns out that the Cantu-Carrère map is an isomorphism from the endomorphisms of LGM to check LGM of R, and this gives us a way to describe the endomorphisms of this group functor in terms of some double Laurent series of a special form. And just a couple of words about the idea of the proof. It uses a canonical decomposition of the loop group of multiplicative group. Let A be an R algebra, and for simplicity, we assume that it has connected spectrum, so it cannot be decomposed into the product of rings. Then the group LGM has the following subgroups. So the first subgroup is Z of A. It is just generated by the formal variable T. The second one consists of invertible constants. And V plus of A is defined to be the subgroup of Taylor series with zero coefficient form. And V minus of A consists of Laurent series of the form 1 plus sum of BI to the ith power, where all the coefficients are nilpotent. And it turns out that the loop group of GM can be decomposed into the product of these four, the direct product of these four subgroups. And it can be seen that Cantu-Carrère map actually commutes with inverse limits. In particular, it commutes with direct products. Therefore, it is sufficient to establish Cantu-Carrère theorem for each factor separately. So for GM, we already have that by the classical Cantu-Carrère theorem. For Z, this is for the constant shift. It is not very difficult because just there are no many morphisms from LGM to Z, and V plus, and for V plus and V minus, the logarithm map is used. So we substantially use the assumption of the Q algebra. So V plus is mapped, the logarithm maps V plus isomorphically to the additive group of Laurent series, of Taylor series, starting with I equals 1, and the minus is mapped isomorphically to Laurent series of the form bi to the ith power, where bi ranges from -n to -1, and all the bi's are important. And so this thing is an infinite direct product of the additive group, and we can pass to the direct limit somehow. And probably the hardest thing here is to establish Cantu-Carré theorem for V minus, because it is a direct sum that is direct limit rather than inverse one. And a certain computation is required, but still the theorem holds for this vector. So probably that is all that I wanted to tell you. Thank you for your attention.
Any questions, please?
So is the Cantu-Carré simple or what? A generalization of some classical symbols.
Yes, as I said, it is.
Could you please indicate what classical results you generalize?
So I started with the chain symbol, which is a rather classical object from algebraic number theory. So and Cantu-Carré symbol is just a way of generalize the same symbol for an arbitrary ring.
Thank you.
Thanks, our speaker again. Thanks to all speakers of our first session today. Now we're going to have a break for like 30 minutes. And we come back at 1 o'clock on Moscow time for next session. Thank you very much.
Hello, can you hear me?
Okay, while we did not start it, I would like to say that it's a special pleasure for me to chair this section where all the speakers are my friends from the first year of our study. Okay, there are a lot of other our friends in this conference, but it was impossible to unify all of us into the one session. However, I think it's some special sign. Okay, so probably it's time to start, and our first speaker today is Anna Felikson from the Durham University. She will speak about Friezes for a pair of pens. Please, Anya.
Thank you. First of all, of course, I want to thank the organizers for this wonderful conference and for the opportunity to participate in congratulations of Georgy Borisovich. I don't have any early story from childhood about Georgy Borisovich, but I have some recent recollections from several years ago when I was invited to speak at this Wednesday seminar, and I was sort of uncertain what I should tell and why it will be of interest. And I came and asked whether I need to tell this story or that, and then Georgy Borisovich started to ask me and made me to tell first the first story, then the second story, then part of the third story, then some parts of the fourth story, and this lasted like for about 4 hours or more. And I need to say it was sort of a unique experience. I had never received such an amount of interest from anywhere else, I would say. So I'm sure that many people here in this conference shared this sort of experience, but for me it was I never got it from anywhere else. So let me now try to speak a little bit about mathematics. It will be some very small story and maybe a very insignificant small result, but it is, I really like to speak about this because it is about Friezes. So it is a small result which we obtained with Ilke Chenaki Anna Garcia Elsner and Pavel Tumarkin last autumn. And why I really like to speak about this, because I have first learned about Friezes in this early year at some conference of Tournament of Towns. So the idea was that we were given some questions to think about them for a week, and then one of the questions was about Friezes, and I really liked that, but I was completely unable to make any advances in that. And then the situation continued like for many years. I really liked the story about the Friezes and tried to follow some new additions to that, but I was never able to say anything from myself. So this is my sort of first result in this direction, and that's why I like to speak about that. So what are the Friezes? So Frieze patterns is something introduced in early 70s by Carl Cockstar and John Conway, and it is a sort of a table like here, which you build in the following way. You write a row of ones, and you write another row of ones, and then you connect them with a zigzag of ones, like here. And then you want to complete the whole table using the following rule. Once you see a diamond, you want it to be unimodular. You want AD minus BC to be 1. For example, you see a diamond here, so 1 multiplied by 2 minus 1 multiplied by 1 should be 1. That's why I put 2 at that place. And then I start to I continue to fill the table. I can put this to here in this diamond, this to here in this diamond, and here, and then I can put purple numbers, and then I can put this red numbers, and so on, and then I will be able to fill the whole table. Why this game makes sense and why is it interesting? Because this table has nice properties. The first property is that after several iterations, one will find out that there is another zigzag of ones, and there is a very similar zigzag of ones here. So this table is going to be periodic. Moreover, one can notice that this zigzag is very similar to this, so it actually also has additional glide symmetry. Also, this table is now we see the whole period, so one can claim that the whole table is filled by integers, and they are positive integers. And I mean, if I look at the diamond rule, I can compute this number d, additional number d here, and it's not a big surprise that it is that the number we obtain is positive, but it is a surprise that it is integer, because when you you divide, when you divide, you can get any rational number, but you only get integers. This is what Conway and Coxeter introduced, and the first thing why it is so nice is that Friezes turned out to be connected to triangulated polygons. So if I have a Frieze pattern with n non-trivial rows, so here it is 5 non-trivial rows, non-units, then I draw an n plus 3 octagon here. And what I want to do, I want to triangulate this polygon in some way. Now, let me count the number of triangles at every vertex. So here at this vertex, I have 1 triangle, then here there are 3 triangles, 1, 2, 3, and here there are 4, 1, 2, 3, 4, and so on. And these numbers, I label all the vertices by the numbers of triangles at the vertices. And these are the numbers I will see in the table here. So I read it 1, 3, 4, 1, 2, 2, 3, 2. And it is here 1, 3, 4, 1, 2, 2, 3, 2. And of course, when I start to continue reading this periodically, I will get a periodic thing in the table. So this connection already, of course, I did not explain yet the whole connection between the table and the triangulation, but this already gives some hint why it is going to be periodic. So, periodic, yeah. Now, what is really the connection? The connection is that every single number, every single position at this table actually corresponds to some diagonal. I was trying to draw here what are the diagonals. So, for example, this is the diagonal here, and so on. And in particular, so in particular, the diagonals in this triangulation, I was trying to draw in red, and they make this zigzag here on the table. Now you might ask me where is the boundary of this triangle, and the boundary is exactly on the boundary of the table. I tried to make the corresponding boundary sides blue, like this is this side 3, 4, and so on. Now, what we can see also in this table is that when we move along a row, the picture rotates by one step, like from here to here, from here to here, and so on, and from here to here to here to here, and so on. The picture always rotates by one step. Numbers in Frieze correspond to diagonals, and now I can ask myself, what are the diamonds? Because we have this diamonds rule, which we want to use to build the Frieze. So what are the diamonds? Since I move every time by one step, one can see that these are quadrilaterals like this. There are two boundary sides and 4 diagonals with this sort of ends. Now, what will be the diamond rule itself? The diamond rule will be the Ptolemy theorem for this quadrilateral, called Ptolemy theorem. So here is the Ptolemy. So the theorem says that if you have a quadrilateral on Euclidean plane inscribed into a circle, then the product of diagonals is equal to the product of 2 opposite sides plus the product of the 2 other opposite sides. And here, what we see, the product of diagonals AD, it is here, is equal to the product of 2 opposite sides 1 and 1, because they are boundary sides. Here is 1, and minus BC here. So this is exactly the Ptolemy theorem for this quadrilateral, assuming that all boundary sides are labeled 1. Now what are we doing really when we build a Frieze? We take a polygon, pick a triangulation from this polygon, then assign ones to all the boundary sides, and suppose we assign x1, x2, x3, x4, and x5 to the arcs of the triangulation. Now we can start to compute all other diagonals just using Ptolemy step by step. So, for example, from this quadrilateral, I can compute this green diagonal by this green formula, and then I can proceed to the next quadrilateral and compute this purple diagonal by this purple formula, and so on. I can continue and compute any given diagonal in this polygon. And what I get from this, I mean, every application of Ptolemy is corresponds to resolving one of the crossings, and every time I will divide by the corresponding variable by the variable corresponding to the arc which I'm crossing. So what I will get something with denominator x1 multiplied by the x2, x3, x4, x5, where x1, x2, x3, x5 are all the diagonals I have crossed by this arc. And of course, if I start with setting all these xi's to be equal to 1, the thing by which I'm dividing is 1, which explains that what I'm getting for every arc is an integer number. So we also explained integers. And moreover, if one can compute even the numerators for these arcs, and this is something done by Ralph Schiffler. And basically, the formula says that the numerator is also counting something, so it's the sum of some positive monomials with some positive coefficients, and in this sense there is a positivity of the numerator also. So what we get is that our picture corresponds to our frieze corresponds to triangulated polygon with ones on the boundary and ones on the diagonals in the triangulation, except that in Euclidean polygon we are unable to set all these diagonals 1. If I set this diagonal x1 to 1, then if in Euclidean polygon it will say that this triangle is the whole of the polygon. I cannot have, if it is quadrilateral or something bigger, the diagonals are not having Euclidean length 1. But it's not a big problem because we actually can use hyperbolic geometry instead. So what we do, we use hyperbolic version of Ptolemy theorem. So this was proposed by Penner in late 80s. And so let's consider a hyperbolic plane in upper half plane or in disk as you like. And let's take 2 points on the boundary. And of course, the distance between them is infinite. But let us still try to measure the distance between A and B by choosing some horocycles at A and horocycle at B, and computing the signed length between this signed distance between these horocycles. I'm saying signed because if these horocycles intersect each other, then I will say that this length is negative. So I will take minus this length. So I get some value L, and I can compute exponent of half of it and call this lambda length. And the statement is that this lambda lengths correspond, these lambda lengths satisfy a Ptolemy equation. So the product of the green ones, of the diagonals, is equal to the product of blue plus the product of red. What do we want to do with this? We can take an ideal triangle and we can choose any 3 numbers, lambda 1, lambda 2, lambda 3, and then there will be a unique choice of horocycles for this triangle so that the lambda lengths of the corresponding sides will be the numbers of our choice. This means that given a triangulated marked surface, so if I have a surface with marked points and triangulation, I can choose any numbers and assign them to arcs of the triangulation, and then there will be a unique decorated hyperbolic structure on this surface such that each triangle is ideal and all lambda lengths of the arcs correspond to the numbers of my choice. by decorated hyperbolic structure, I mean there is a unique choice of Hara cycles on this surface, which means that we have resolved our problem that Euclidean in Euclidean polygon we could not take xi's to be ones. Now using this hyperbolic model, we can take any numbers, including ones on the boundary and ones on the diagonals of the triangulation. And from now on, we will understand the Frieze not as a table, but as a map from arcs to real numbers. But we want this map to satisfy Ptolemaic equation. So from now, a Frieze is a map satisfying Ptolemaic equation. And one statement from Conveyan and Coxeter is that every positive integer Frieze, so positive Frieze with positive integer numbers, with finitely many rows, actually arises from a triangulated polygon with ones associated to diagonals in the triangulations and ones on the boundary. And this is the theorem that we wanted to generalize. So now let me give a little bit more general definition. It is known since 70s and was actively used in the recent years because of cluster algebras, but I'm going to discuss this definition only in the context of triangulated surfaces. So let me take a surface, let me take finitely many marked points on this surface, so that there is at least one marked point at every boundary, because I want to triangulate the surface, and I triangulate the surface by arcs with vertices at these marked points. Now, given the set of all arcs on the surface, let me define the Frieze as a map 5, which takes every arc to some real number, so that a Ptolemaic relation will hold for every quadrilateral in on this surface. And I will also call the Frieze positive if it maps to positive numbers, and integers if it maps to integers. So I will keep these definitions here. And just to remind you, that if we speak about positive Friezes, then lambda length of on hyperbolic surfaces gives us a universal example of a Frieze. So we can just think about triangulated surfaces instead of Friezes. Now, a Frieze is also called unitary if there exists a triangulation such that on every arc of this triangulation, the Frieze gives 1. And one can ask, given a marked surface, is it true that every positive integer Frieze is unitary? So given a Frieze, is it true, or Frieze for this surface, is it true that we are able to find a triangulation on which this Frieze gives 1? And this is exactly the question answered by Conveyan and Coxeter. So yes, if the surface is a polygon, then we do know this, the answer to this question. And one could think that this is the situation for which we have always, but no. If the surface is a punctured polygon, then the answer is no. So the Frieze itself in that case looks a little bit different from what we. I mean, it's it can be still written as a table, but I mean, one cannot find a triangulation on the surface so that all arcs will be labeled 1, if you want to the Ptolemaic relations to be satisfied. Then there was a result by Ganavan and Schilfler saying that if S is an analysis with any number of marked points on the boundary, then the answer is yes. And the next reasonable small surface to look at was pair of points, and this is what we did. So let's take a pair of points and take any number of points at every boundary component. And then we claim that every positive integer Frieze on this surface such that it is one on all boundary arcs, then this Frieze is unitary, which means that one can find a decorated hyperbolic structure on this pair of points. This means that given any decorated hyperbolic structure on this pair of points, so that the boundary arcs are of length 1, one can find a triangulation with lambda length of every arc in this triangulation to be equal to 1. One remark is that if such a triangulation exists, then it is clearly unique, and this follows more or less immediately by Ptolemy. So this is the statement. This is more or less whole of the proof. If to say it in 1 minute, we first reduce the surface by cutting out unnecessary bits. If you have some boundary or some peripheral arc of length 1, you can just cut out this polygon and use smaller surface, smaller pair of points, and the result of conveying Cox etc. here. And then we cut our pair of points along shortest bridging arc, connecting two different components, and either we get some, either the length of the shortest arc was 1, and then we use the result by about the annulus, or this length was bigger than 1, and then we need to do something which we choose some specific triangulation, taking the shortest bridging arcs 1 by 1, and building some triangulation on this annulus, and then we apply Ptolemy relation to show that if we start from some point, the lengths of the lambda lengths of the arcs will grow when we move, but since we are on the annulus, they cannot always grow. They should come back at some point. So this is impossible, which means that we are actually in the situation when, this situation is impossible, which means that we always have some unitary triangulation. And this is more or less what I wanted to say, except that like some final remarks that, of course, I mean, I was a little bit cheating. We need to do some case study. But it's really like very short and easy, and in this way we can reproduce the results for polygons and annulus, and also we can speak about quiddity sequence for every boundary component, like the lambda length of such an arc will be the number of triangles crossed by this arc. And we were very excited when we started to do that, because we thought that now we are going to do all the surfaces, but in reality we failed to extend this proof to any other surface. So I mean, we tried some small things like just a handle with one boundary point, or genus one with four boundary components. So we were just unable to do anything. Our induction step was not working. And we even don't know whether it is true or not. So no guesses at the moment. And finally, if you don't know much about Friezes and like this as a topic, so there is a very nice survey by Sophie Marie Genoud. Yeah, and this is really what I wanted to say. Thank you for listening, and happy birthday to Georgi Boris.
Great.
Thank you.
Thank you very much, Anya, for this very interesting and beautiful talk. Does anybody have some questions or comments?
Well, I have perhaps a remark and a question. Anya, thank you for the congratulation and for a fantastically clear talk on the fantastically beautiful mathematics. Just a small detail, perhaps noticed by everybody, is that your slides are presented with in a beautiful and very clear handwriting, quite a rare thing nowadays. Now I have a mathematical question, just to hear maybe your answer. Is it crazy enough? It needs a short introduction about the moduli spaces of curves presented as a union of cells, well, times real octants, by union of cells labeled by the Sandom form. These structures are understood in terms of meteorizable ribbon graphs. And as we know, we can use two kinds of geometry, the piecewise plane Euclidean geometry and the hyperbolic geometry that you were using. We know by Molyakov and Kava that in the case of piecewise Euclidean geometry, the structures corresponding to integer natural lengths of the edges are related to the arithmetical curves, the curves over Q bar. Is hope for similar results crazy? I mean, results that may be in terms of Friezes or some they're more complicated analogs is the hopes crazy that we can find arithmetic also using hyperbolic geometry? That is the question.
Yeah, I mean, very interesting question. Obviously, I have nothing to add here at the moment. Yeah, but yeah, looks very interesting. Mm-hmm. Yeah. And maybe one question to the audience. I don't know. I mean, I forgot to state that I was not able to recall who was that person in 1990 who told school students about Friezes on the conference so if someone can tell me the answer to that, it will be fantastic, because I wasn't able to find that person.
Okay, let's think again. Anya? And our next speaker today is Pavel Tumarkin. Hi, Pasha. We are going to hear about Quivers surfaces and the reflection groups. Please.
Okay, thank you. Let me try to share my screen. Okay, so after having seen previous talk with the nice handwriting, you will be exposed to some different handwriting. Sorry for that. Okay, so but first of all, so I would like to thank Georgi Borisovich and the organizers of the conference for inviting me. It's a real honor to speak here. And I also wanted to say, so concerning the somehow youth recollection, that many years ago, Georgi Borisovich has helped me a lot in mathematics, because at some point I shared with him the problem I was working on at the moment, and actually I was working on that problem for an extensive period of time already by the time, and Georgi Borisovich expressed some doubts whether this problem is solvable and whether somehow it was not already proved to be incorrect. And of course he was right. The problem was already proven to be incorrect. And actually, so this saved me from future pointless years of research, and so I could switch to something else. And it really had a very, very big impact on my mathematical life and my future mathematical life. And I'm really grateful to Georgi Borisovich for that. Okay, so this is something about that. And now let me go to mathematics. So the title of the talk is, as you can see, Quivers, surfaces and reflection groups. The talk is supposed to be completely elementary, so please stop me if something is unclear. There's no deep moral here, just some observations, mostly of geometrical nature. But I should also say that somewhere in the background, there are cluster algebras and quivers and mutations, and in particular, a very, very long and still ongoing project joined with Anya, Felikson, and Misha Shapira. The project is on realizing mutations in cluster algebras as reflections in some quadratic spaces. The project is long and without any indication that it will end at any point. But, and of course, I cannot fit it this long story in half an hour, but some self-standing bits of it and some applications which arise on the way. Okay, so I start with a surface with boundary, and surface is with there are marked points on the boundary of the surface, and as you have already seen in Anna's talk, and T is the triangulation of this surface, and what we want to get a group by this date. Yeah, so we have a surface with marked points on the boundary, and such that on every boundary component there's at least one marked point. We have a triangulation with vertices at marked points, and we want to construct a group by this data. Okay, so instead of telling you how to do that, I will show you an example. And so the easiest example when our surface is a polygon. Yeah, so I take a hexagon and I take two triangulations of it. So this is T1 and this is T2, and there are actually there are only three possible triangulations, essentially different triangulations of hexagon. So I show two here, and then by triangulation I construct a quiver, so-called adjacency quiver of a triangulation. The way to construct a quiver is the following. So the vertices of the quiver correspond to diagonals so of my triangulation, or equivalently to arcs of a triangulation on any surface. And the arrows between the vertices, so there's an arrow between two vertices if these arcs of triangulation lies in one triangle and one of them follows in clockwise direction there. Yeah. Then we put an arrow. For example, for T1, we get this red quiver. So here it is. Yeah. And for triangulation T2, we have a cycle consisting of three vertices. Okay, so we got a quiver. Yeah. And now by using this quiver, we want to construct a group. So how do we do that? So this is done in two steps. So the first step is that we forget about orientations of the arrows on the quiver and treat this as a graph. Just we consider the underlying graph of that. And then we treat this graph as a Coxeter diagram of a Coxeter group. Namely, we put a generator for every vertex of the graph. So in this particular case, we have three generators, S1, S2, S3. And we add relations. The relations will be the following. Let me write. So these are relations so far. So the first is that every element is an involution, like in the Coxeter group. This is reflection. Yeah. And the second, that for any two generators, there's a relation as I as j to the power mij, where mij is defined in the following way. Yeah. So that mij is 2 if the vertices are not connected by an edge, and mij is 3 if the vertices are connected by an edge. So in this way, we get a Coxeter group like that. Yeah. And then we add additional relations, which we call cycle relations. Well, as you can guess, the word cycle relations, they correspond to cycles in the quiver. They correspond to oriented cycles in the quiver. And here we remember that this is not a graph, this is a quiver. Okay, so all edges are oriented. And the rule is the following. So for every cycle, if we have a cycle of length d, yeah, we add the following relation. We write S1, S2, and so on to SD. So we go along the whole cycle, and then we go back. But we go back not to the end, but to S2. Okay, so in other words, this can be understood as the following relation, that S1 commutes with SD, which is conjugated by all that, by the product of all that. Okay, so this is my group. Let me write that this is G of ST. Yeah, and let us look how this group looks like in these two particular examples for these two triangulations. So in the first case here, we do not have any cycles. So we have just Coxeter group. This is Weil group of type A3. So this is symmetric group on permutations of 4 elements. Yeah, and in this case, there's additional relation. This is indeed the cycle relation that we should take 1, 2, 3, 2, and take a square. Okay, so these are relations. This is for the left triangulation, T1, and this is for triangulation T2. So here I call them S. Yeah, we see that we have S1, S2, and S2, S3 cube, and S1 commute with S3. Yeah, here it is. If you can really see that this is 3 and not 2. Okay, and on the right, for this triangulation, yeah, we have the following group. We have TIs. All of them are involutions. Product of each of them to the power 3 is identity. And we also have this relation 1, 2, 3, 2. squared. Okay, so we get two different groups. Well, they're supposed to be different, but they are not, because actually they coincide, and one can easily see these by changing generators. If we, instead of S, we write S1 to be equal to T1, S2 to be equal to T2, and S3 is just conjugate of T3 by T2. Yeah, we see that instead of these relations on the left, we get relations on the right, or opposite one. So the group is actually this, and this is not an somehow an occasion. There's a theorem by Mikhail Barod and Bethany Marsh, which says the following: that if our surface is n plus 3 gon, a polygon with n plus 3 vertices, or an n-gon with one puncture in the center, yeah, and we take any triangulation of the surface, we construct the corresponding group, yeah, and then the statement that for any triangulation of the surface, the corresponding group will be either Y group of type AN for the polygon, or Y group of type DN for one structured polygon. Okay, well, respectively. Okay, so actually this group does not depend on triangulation. Okay, so if we change the triangulation, that we don't change anything, and probably a side remark that in terms of quivers, or that change of triangulation correspond to flips, and the flips are precisely mutations. So the statement says that the group doesn't change under mutations. Okay, so this is some, of course, the theorem by Barod and Marsh. So it is formulated in much greater generality, though. So, but I try to keep everything simple, moreover simple-laced for the groups, and also I use only classical. Classical Coxeter groups, because they have results for all finite Y groups. Okay, so this is about the group, which is the same for polygon. So for every polygon and for all triangulations. And now I want to say a couple of words about some geometric, that these result has a nice geometric interpretation. Geometric interpretation is the following: that we, as you can see here, we look at our group in the following way. First we have a Coxeter group here, yeah, and then we add some additional relations. So we can say that our group G, yeah, is a quotient of a Coxeter group by normal closure of these additional cycle relations. Okay, and this Coxeter group, for Coxeter groups, well, everything, well, a lot is known about Coxeter groups, and in particular, that Coxeter groups act on always act properly, discontinuously, and I would say nicely, on some good good simplicial complexes. And sometimes they're even nicer than they can act on manifolds, for example, on hyperbolic space, with fundamental domain of finite work. And if this is the case, and our group G is finite, then we see, so what we get? We get that this normal closure, yeah, is a finite index subgroup of our Coxeter group. Yeah, and then we can take a quotient, and we can get either orbifold or manifold as a result. So let me show you example concerning precisely this triangulation. So we start with our group with our triangle, yeah, and this is our group, okay. And then first we look at these part as this Coxeter group, and we see that if we look at just as the Coxeter group generated by this S1, S2, S3 with these relations, then this is a group which is generated by reflections of equilateral triangle on the Euclidean plane. Yeah. So and each SI is a reflection. So and then so this is the picture, yeah, of the plane, and then we add this relation, let us look what this relation means. Yeah. So we have S1, and S1 computes with S2, S3, S2. Yeah. So what is S1? S1 is so here I have 3 reflections, 1, 2, 3. Yeah. So I have S1 is this, and then S2, S3, S2 is reflection with respect to this line. So I have these 2 reflections, and their product square is equal to identity. So what is the product of 2 reflections and 2 parallel lines? Is a translation by 2 levels. Yeah. The square is a translation by 4 levels. Yeah. And then I say that this is identity, which means that I need to identify this line and this line on this picture. But since I have normal closure, I have also rotation by 2 pi over 3 in my group. So I need to identify these and these. And I also need to identify these and these. What I'm left with, after I glue what I got, I have a torus, which is tessellated by 24 triangles. And my initial group, which is wild group of type A3, yeah, acts by permutations on this triangle. Okay, so it is not action by reflections, but well, we started with some finite group, and we got a torus with somehow with an action of this finite group. Well, for torus, it's not too surprising that we can find an action of some group. Yeah, but these can be, so this construction, this general construction can be generalized. Yeah, and in particular, this a result of Aine and myself. Yeah, that what we proved that in this particular case, when we start with a polygon, yeah, that normal closure of these cycle relations is a torsion-free subgroup of this Coxeter group, which means that if this group is finite, yeah, then what we get after quotient, we get a manifold. Okay. In particular, so here a couple of examples which we can get. If we start with 7-gon, with the heptagon, heptagon has a triangulation with the following group. But if we forget about orientation of the arrows, this graph corresponds to a hyperbolic simplex, which tessellates, or finite volume, which tessellates the space. So when we apply our construction, we get a 3-dimensional hyperbolic manifold. Yeah. Well, this 3-dimensional hyperbolic manifold is not new, so it was known before. But if we can do exactly the same with the decagon, yeah, it has a triangulation with this quiver. Well, this is not a quiver, this is a graph, but you should orient both triangles such that they are oriented. Yeah, and do exactly the same construction. And what we get a 5-dimensional hyperbolic manifold with huge symmetry group. Symmetry group contains the wild group of type A7, yeah, which is symmetric group on 8 elements. Yeah. Of course, again, these can be generalized. This could be applied also to further finite Coxeter groups. Yeah, but probably this is somehow in some to a different side. Yeah, and now this was just an application. Let me go back to my group from a surface. Now let me generalize it and construct this group for any unpunctured surface, so that a surface with mark points on the boundary only. Yeah, this is exactly the same construction. You take the quiver, we forget about orientation, we take a Coxeter group, and then we add relations. But we need to add some more relations. Okay, so the relations which we add are the following. If we meet on our way in the quiver this subquiver, like that, we add this relation, so we interpret it as a cycle, but here the power is free. Yeah, if we meet these subquiver, we also treat this as a cycle. And if so, this corresponds to an anomalous with 2 points on one boundary and one on another. This corresponds to a boundary with 3 points on some on one side, and yes, and one on or probably 2 and 2. Yeah. Yes, this corresponds to an anomalous with 2 points on each boundary component. Yeah, and these one more relation, this we call it handle relation, because this corresponds to triangulation of torus with one hole and one puncture. And one marked point on the boundary. Yeah. So again, we get a group for any triangulation. And then the theorem, also by Anne and myself, that this group does not depend on the triangulation. Yeah. We always get the same group. And moreover, somehow the isomorphism between these groups, it also it looks like here. We always have one element conjugated by others. So we still have, in other words, what do we have? We have some reflections in some initial reflection group, yeah, but just different collection of reflections. Yeah. What can we say about this group? So we somehow prove that this is an invariant of a surface. The problem that it is not a Coxeter group anymore. This is some quotient of a Coxeter group, and but this is not all. Actually, we cannot say much about this group, and till some point we even couldn't prove that this group is not true. Because what do we have? So you have a Coxeter group, you have many relations, and well, it's not quite clear why these relations do not degenerate the group completely, right? And we use some different techniques, some computational techniques, but nothing was working. And what actually helped in the end was construction of another group. So what I want just to tell you now is a construction of another group, also from unpunctured surface. But this is a known, known not related to surface, but just known abstractly. This is so-called extended affine Y groups. These were studied by, let me add this probably, by Moody and Saiter, yeah, and many of their students. So what we're doing is the following. I take my surface and I take very, very particular triangulation of the surface. The triangulation is organized in the following way. It has at least one boundary component. So this is my boundary component. On this boundary component, there's at least one mark point. This is my mark point. Yeah, and probably it has more mark points. I'm not sure. If there are, I cut them off by an arc X, which so I call it X. I may have some holes, other boundary components. Yeah, I cut them off also by another arc, and I may have some handles. I also cut them off by another arc. So what I get as a result, yeah, I get a quiver of the following type. I get my vertices X, Z, and Y, and arrows like this. Yeah, and then I have bubbles. I have a bubble here, I have a bubble here, and I have a bubble here. Yeah, where this bubble corresponds to triangulation of this polygon. This bubble corresponds to triangulation of this monogon with handles. Okay, so this is a surface with of some genus with one boundary component and one mark point on here, and this bubble corresponds to triangulation of this surface of genus 0. Yeah, with some boundary components. Yeah, so as an example, well, for the polygon, I can just triangulate it such that the corresponding quiver will be linear. This is, for example, I take triangulation such that all diagonals come from one vertex. For this bubble, so for this monogon, so I have shown an example of triangulation which I can use. Yeah, so again, I somehow cut off every single boundary component and somehow triangulate it inside. Yeah, so it's a bit technical, but overall, I get a very, very, very specific triangulation. Yeah, and for this triangulation, I got quiver which looks like this. Yeah, so this is my triangle. This is my bubble for X. This is my bubble for Y, where every such picture corresponds to boundary component, and this is the somehow part for the handles, where every such quiver, subquiver, corresponds to a handle, to additional gems. Okay, so I got this quiver. What to do next? And next I will do the following. Let us suspend for a while some vertices of this quiver. Okay, so I suspend all ends of the double arrows for every handle, and I suspend one vertex of every double arrow corresponding to boundary component. After I remove this, I got a still big quiver. Yeah, so I removed 2G vertices here, and I removed B minus 1 vertices here, where B is the number of boundary components. But then something surprising happens, that this big quiver occurred to be a quiver which originates from a triangulation of some polygon, which follows from a result of Taylor-Henry. Yeah, so we can somehow we can find a big polygon, yeah, and its triangulation such that the corresponding quiver is like that. What does it tell us? It tells that we can assign to every vertex of our quiver a root of the root system AN, as we have done before. Okay, we had our symmetric group, yeah, originated from such quivers, so the generators were reflections, or instead of reflection, we can just put a vector, right? So let me do this. Yeah, so I assign vectors VIs, and so somehow here to every vertex, and then so what we got collection of roots of the system root system AN, yeah, and we can interpret them as a quadratic space. So this is the basis, yeah, and the quadratic form is a Gram matrix of these vectors, right? And then to this quadratic form, and to this quadratic space, I add many additional vectors. So how I do this, I add the elements of the kernel. So if this is VI, for example, then here I add VI plus delta I, where delta I will be an element of the kernel of the quadratic form. And here, if this is, for example, VI and VJ, I add VI plus VJ plus delta 1, and here also I get the same plus delta 2. Okay, so I add. So what I have done, I added a lot of kernel vectors, and also I add the dual ones to these delta I prime, yeah, such that the inner product with delta i's is 1, yeah, and with everything else is 0. Okay, so they are not anymore the kernels, so I extended my quadratic form, and this corresponds to extended affine value. This is why it's called extended, and so what we get extended affine root system and the corresponding extended affine Y group, which acts by reflections, so this group generated by these reflections, yeah, in these vectors, and acts on these big space. Yeah. So this group is somehow studied. Well, it's known at least that it is not empty. It's not trivial. Yeah. And what we proved with Anya, with John Lawson, and with Misha Shapiro, so that for this triangulation we have two groups. Yeah. We have group G of ST with generators corresponding to vertices of a quiver, and we have group W of S with generators corresponding to vertices of the quiver. If I write SI here, I write TI here. I send every SI to TI, and our theorem says that this map can be extended to a surjective homomorphism. So our group actually is not less than these well-known extended affine value. So we know at least something about our group. Moreover, just some final remark, that for the case when the surface is a polygon or an anomalous, these groups actually coincide. So this group is the same as this group. And actually, we were looking for a kernel in bigger cases. We haven't found any kernel so far. It doesn't mean it doesn't exist. Yeah, but somehow we have some weak conjecture and weak hope that these groups are actually the same, but I'm not sure that this will be somehow good outcome of this activity, that we somehow, this will mean that we haven't found any new group. Yeah, but at least this will add some understanding. Yeah, and again, so I want to say that so these results can be formulated in bigger generality. Instead of surfaces, we can use for orbifolds with points of order 2. Yeah, in some other directions. Okay, and this is all I wanted to say. So thank you, and happy birthday to Georgi Borisovich again.
Thank you, Pasha, for a very interesting talk. Actually, we almost have no time for the questions, but if somebody wants to present a very short question, you are welcome.
Is this construction applicable for large dimensions and Coxter groups in large dimensional Euclidean spaces with reflections over hyperplanes? And what are these normal subgroups of the usual Coxter group?
Well, this is a good question. In Euclidean space, I do. Well, if we start with a punctured, once punctured polygon, so this means that we start with a Y group of type Dn, then we will always get a torus of dimension n-1. So this will be a group, the group of translations. This is what happens in Euclidean space. Where what happens in hyperbolic space, it's more tricky, and one should look at every particular case separately.
Okay, let's thank Pasha again. Thank you very much. And our next speaker is Alexander Guterman, who will talk about maps preserving matrix invariants. Sasha, please, we're hearing.
Good afternoon. I believe it's my pleasure to speak here on the birthday of Georgi Borisovich. So first of all, happy birthday, Georgi Borisovich, to you. And I will be talking about maps preserving different matrix invariants. The history of this topic goes back to the work of Dedekind. He was considered the following problem. Assume we have a finite group, say G, and its order is some n, when we could consider its table of multiplication, or what is sometimes called Cayley table. So here we put the products between elements xi and xj on the intersection between lines I and j. If we consider this Cayley table as a matrix, then working in the free algebra, we could consider its determinant. So we denote elements of our group by commuting variables, and we respect all the laws from the Cayley table here. So it is the determinant of this matrix. Sometimes it is called group determinant. It is a certain homogeneous polynomial of degree which is equal to the order of a group. Frobenius, actually Dedekind, was interested in decomposing this group determinant, this polynomial, into the product of irreducible factors. And in particular, if our group is finite and abelian, then he proved that group determinant, the determinant of a Kelly table, could be decomposed into the product of linear factors. And the number of factors is, of course, coincides with the order of a group, with the degree of a polynomial. But this was only in the abelian case. For example, let me show this on the following simple example. We have a cyclic group of order 3, and we consider its Kelly table. So, and here I just put here variables x, y, z for 0, 1, and 2 correspondingly. So the rest of variables are filled according to the law of multiplication in this cyclic group. Then the Kelly table has this form. And if we would like to decompose it into the product of linear factors, the decomposition will be as follows. So this is our determinant, the determinant of this matrix, just computed simply by definition, and assuming that multiplication of variables is commutative. Then, moreover, we could decompose this cubic polynomial into the product of 3 irreducible factors written here, where epsilon is the root of unity. And actually there is a correspondence between factors here and another famous table related to the finite group, namely the character table. The character table, actually the rows of character table, here you have irreducible characters, and here you have conjugacy classes, and you evaluate these characters on the conjugacy classes in the character table, and you see there is a correspondence between rows of character table and coefficients of linear factors in this decomposition. So they are nothing but values of characters. They are nothing but the coefficients in a certain linear factor of this decomposition. So this was a abelian case, and the theorem by Dedekind was proved for abelian finite groups, and he was trying to see what will happen in the non-commutative case. Even working with small non-commutative, non-abelian groups like quaternions, permutations, already lead us to non-linear factors in the decomposition. So Frobenius was trying to prove that decomposition to the linear factors exist, but over some more general hypercomplex field. At those times, it was not the theorem of Frobenius about non-existence of such fields was not proved yet. So Dedekind was going into the wrong direction, trying to prove that decomposition is always linear, and was stuck and was asking around what is happening in the non-commutative situation. In particular, he asked Frobenius about that. And after some 16 years, it was Frobenius who solved the problem completely. So for any finite group, there exists a decomposition of group determinant, just the determinant of a Kelly table, such that this is a decomposition into the product of irreducible polynomials. And the general phenomenon is that degree of each polynomial is nothing but the multiplicity of this particular polynomial in the decomposition of a group determinant. There is also a relation with characters. I will not go into the details here, but I would like to point out that this was proved in the same paper where Frobenius created the representation theory of finite groups. In order to prove that a certain uniqueness for this result, namely, we could always ask, assume we have two equivalent representations. Do they correspond to the same irreducible factor here or not? To show that the answer is positive, it was necessary for Frobenius to decompose, to consider maps which will simplify the matrix he was working with, while these transformations were preserving determinant. So it was necessary for him to find out what are these maps on matrices which preserve determinant. And this is his result. Over complex numbers, he was considering quadratic square matrices and linear and bijective maps preserving determinant. So such a natural question is, what are such maps among linear and bijective which will preserve determinant? Do we know them? Certainly, there are naive answers for that question. For example, we could always consider transposition. We could always consider similarity. We could always consider actually, so to say, generalized similarity. Here, P and Q are arbitrary invertible matrices with determinant of a product is equal to 1. And the deep result of Frobenius is where he proved that besides these two types of maps, namely generalized similarity and transposition, and of course all possible compositions of these two maps, there are no more transformations preserving determinant in the linear case. So the opposite direction is a deep result of Frobenius. Well, later on, this result was generalized to Schur for minors. He was considering subdeterminants and maps preserving all matrix of subdeterminants, and also characterized such maps for a given R, I mean the order of subdeterminants. Later, this was also generalized by Dieudonné. He was considering the zero locus of the determinant. So maps which preserve the set of singular matrices, namely singular matrix must be sent by our map to another singular matrix. So this is the restriction. And in addition, we assume again linearity and bijectivity. And it turns out that these maps have they have certain standard form. They are either of this type with two invertible matrices, or in addition, the transposition could appear. Again, it is evident that these maps are of our form, but it is a deep result to show that there are no more maps preserving singularity. Actually, here, Dieudonné used projective geometry to prove this result, to compare with Frobenius, who was basically using matrix theory. After that, it was Evgeny Borisovich Dynkin who actually used his characterization of maximal subgroup of classical groups to prove similar results. So we have all invertible matrices preserving certain invariant. So we are looking to maps on them, meaning we are inside such a GLN square, and we have certain naive examples of maps we are looking for, maps which preserve certain invariant. The set of maps, the whole set of maps which will preserve this invariant is somewhere in between these two groups. And it is possible to show for many invariants that it is maximal. And there is a characterization proved by, established by Dynkin of such groups. And as a result of this characterization, we could see that there are not so many. There are just few subgroups, maximal subgroups of this type, and by considering all possibilities, it is possible to show sometimes that the inclusion on the left-hand side is actually coincidence, and finally to prove the result. I will not go into the details here, which are many. I will just explain a bit why we need such maps. For example, usually they are called linear preservers. So let us look to the determinant function. We all know that it could be computed in polynomial time by Gaussian elimination. And the reason why Gaussian elimination exists, in fact, goes back to the result of Frobenius. The result of Frobenius is telling us that there are considerably many maps preserving preserving determinant. So they are of this form. And how you compute the invariant, you just reduce your matrix to the certain manageable form and then compute. So here you could do a lot and finally compute determinant in cubic time. But if we consider similar invariant, which is called permanent, here I just ignore the minus sign. Then it is an open problem if there exists a polynomial algorithm to compute permanent. And actually, if this algorithm will exist, then many problems from combinatorial optimizations will be solved in polynomial time. So in general, people believe that there are no such algorithms. But for example, it could be computed by riser formula, not by factorial, time, but by exponential time. And one could try to understand why it happens that for determinant we have polynomial time, and for permanent we do have exponential complexity. And the reason goes back again to the theory of linear preservers. Linear maps which preserve permanent, this is a characterization result of Marcus and May. They proved that they appear very seldom. So diagonal scaling and multiplication by two permutational matrices and transposition, of course, and actually no more maps which will preserve permanent. So what you could do with such maps? Not really a lot. So you couldn't reduce your matrix to a certain manageable form while preserving permanent. And that is why it is actually difficult to compute it, to compare with determinant. Well, there are many other applications. I will skip some of them. We have mentioned group determinant. There was a question, assume we have two finite groups. We could ask what is called usually isomorphism question. So is it possible that two non-isomorphic finite groups have the same group determinant? And this was answered by Formanek and Sibley by application. They actually proved that group determinant determines the group up to automorphism, and in particular solved this problem. But the result was based on Dieudonné theorem for singularity preservers I just mentioned. So in general, we have different invariants or relations or properties, say on matrices, and we are looking for the set of maps which preserve them. Some restrictions on maps, some restrictions on invariants or relations, and some restrictions on coefficients. Sometimes these maps will have certain standard form, like it was mentioned before. Sometimes these maps could be heavily non-standard. For example, there was famous Kapulansky-Watkins problem related to the maps preserving zeros of matricial polynomials, and they actually proved that such maps, say for one variable polynomials, here we have matrices of finite order and corresponding polynomial, and we are looking for zeros of such polynomial, and it appears that maps preserving this set, it could be characterized, this set of maps is hosted by these two types of transformations. But if I for example, proceed with nilpotency, so it was property of matrix to have a finite order, and here I have nilpotency, then maps already becoming non-standard. So we have two components, not only the standard component on the left-hand side. I will skip some other results illustrating the general theory. There are different methods how one could work with maps using many approaches. And I would like to pass to non-commutative determinant preservers in particular. So there was a result by Gisson and Mehta saying that if I have a function on matrices having these three natural properties, so if I have determinant with these three natural properties, then my ring must be commutative. So to work with non-commutative rings, I must remove some of these properties, and this was actually approached by Dieudonné. So he was considering a multiplicative group of a division ring, quotient of this group by commutant, so it is already abelian, and the function which sends matrices to the quotient group by commutant. And he proved that if you assume these three properties here, then indeed there exists a function called Dieudonné determinant which satisfy all of them. There are non-commutative determinants. They are actually useful in many different theories. For example, K theory to define K1 functor. Let me just show you how the characterization results look like. So over a division ring over a certain field, we consider maps which are semi-linear, just in this sense. So if I act on the product with a scalar, I consider the image of certain automorphism here, and then in such case, it is possible to obtain the characterization of such maps. They are either of this form here, or the second form here with automorphism, with semilinear automorphism or semilinear anti-automorphism. And I will not go into the proof details. I would like to mention just that behind this result, I was using so-called coherence preservers. So maps, two matrices are said coherent if the rank of their difference is less than equal to 1. This is actually a very important relation for in special relativity. These matrices represent coherent events in space-time space. But actually behind this result on maps preserving the determinant, there is a characterization for linear maps preserving coherence, which is due to Leonid. I would like also finally mention that it is possible to define a certain rank concept, say over local rings. So local ring is when all non-invertible elements form an ideal, and maybe I will show the final slide presenting the characterization for linear maps preserving singularity over local rings. So this could be considered as a non-commutative generalization of Diedone result on singularity preservers in the generality of local rings. Thank you. I will stop here.
Thank you, Sasha. Just one small question. You told us about determinants of non-commutative rings, and what is about commutative rings? Are there some results of that kind in this generality?
Yes, I actually, it was my mistake not to mention the result of MacDonald and parallel result of Waterhouse, actually presenting the characterization for linear maps on matrices over commutative rings. So in a way, for determinant, these maps are standard in that sense. Yes, this is true.
Okay, are there any other questions or comments?
Yes, perhaps I have one just out of curiosity related to the beginning of the talk. So we could write the something like the group determinant for any, well, magma, or any finite magma that is, well, just a compositional without any restrictions. But there are lots of, other objects like semigroups, Fun groups, and perhaps algebraists know much more. Can you tell by the determinant, by this determinant polynomial, the groups out of other algebraic structures?
Mm-hmm. First of all, I would like to mention that we need two operations to define group determinants. So we need operation in that magma, like in semi-group, but we need also to add the variables corresponding to the elements. But even though sometimes we could introduce both operations, it is not true that say the isomorphism question there is no positive solution of isomorphism question, say in semi-group generality. So this result by Formanek and Sibley explaining that group determinant determines the group up to isomorphism of groups is not any longer true for semi-groups. But I agree with you that it will be good actually to go ahead and to check other abstract systems. It might be that say in some of the cases, say I don't know, nearings, for example, the answer could be positive. I simply don't know at the moment, but my intuition say that it could be that not only group. Yeah, one have to check the other algebraic structures, the other cases of magma, if they, if for example, the isomorphism question could be solved positively there, or it's only the case of groups where it could be solved positively. Actually, nobody looked at it, and this could be, thank you, this could be a good direction to pursue in the future. I completely agree.
Actually, I was interested maybe in a simpler question. Does the group determinant see the invertibility of the elements? So you definitely can write the same determinant for a semigroup.
Yes, but there is no direct relation which will allow to check the invertibility this way. It is not that straightforward, I should say, to check invertibility using group determinant. But it will be interesting to look at.
Okay, are there any other questions or comments?
I have a question. Sasha, you mentioned Razor formula for computing permanent.
Yes.
As I understand it, it reduces the computational complexity from n factorial by definition to n times 2 to the power of n. And
yes,
there is an algorithm for solving travel salesman problem using dynamic programming, complex dynamic programming over all subsets. It does exactly the same. It reduces the complexity from n factorial to the same function. Are they related? Is it known?
Yes, yes. Actually, it was Valiant who was thinking to solve Millennium problem about complexity P and P problem. By reducing it to simple matrices, he was thinking to solve a problem, and then what actually he did, he solved his Camivojor problem. He reduced it to the problem of computing permanent, and then he was stuck because this problem is actually sharply complete. it has there is actually if one could be able to find better algorithms to compute permanent, then one could solve travel salesman problem better as well. Yeah, so these two things are indeed parallel. You are completely correct.
Thank you very much.
Okay, so let us thank Sasha again. And let us also thank the speakers and the listeners of this section. And now we have break.
Okay, dear colleagues, so we start our final session. 3 out of the 4 talks scheduled for it seem formally unrelated to our main domains of the study. However, I think they are quite appropriate in this conference, partially because the speakers are my friends and colleagues, and partially because we are just interested in mathematics, and when we discuss some unrelated subjects, who knows whether some relations can be found in future. So I am happy to invite my friend and relative, Sergei Smirnov, please.
Okay, thank you. So first of all, I'd like to thank the organizers for the possibility to give a talk here. And so, as Georgi Borisovich had said, my talk has nothing in common with the Descent d'Enfants, but still, this is a truly Shabat story, as you will see this talk. Okay, so integral preserving discretization of two-dimensional Toda lattices. So I'll start from one rather simple definition. So let us consider a hyperbolic equation in general. So this could be a vector equation, so u could be a vector. And so the function that depends on x derivatives of the function u. So first of all, I need to say that u depends on 2 independent variables, x and y. And so u is a function. And so I consider hyperbolic equations of this kind where u is a function of 2 independent variables, x and y. And so the subscripts mean the derivatives with respect to x and to y, and the function I is called y integral of such system or such equation if its total derivative with respect to y vanishes. So this means that if we take this function and differentiate it with respect to y, then if we substitute the expression for mixed derivatives, we get 0. So this is, in some sense, this is a generalization of the notion of first integral for ordinary differential equation to the case of hyperbolic equations. And so here is the example. So this is the scalar Liouville equation. So this is the simplest example in some sense, and it is not difficult to verify that these functions I and j are y and x integrals of this equation respectively. So this is just a simple exercise to verify that they are characteristic integrals. So both x integrals and y integrals are called characteristic integrals. Okay, so the main difference between this case and the case of ordinary differential equations is that here existence of characteristic integrals is a very special thing. So if you take some equation, arbitrary equation, it does not admit characteristic integrals. So, for example, if you consider such linear equation, it is not difficult to prove that it does not admit characteristic integrals. So the question I'm interested here in this talk, and this is a rather general question, so what hyperbolic equations admit characteristic integrals? And so now, after we have considered this trivial example, I'm going to move to the next example and to the system I'm going to talk about. So this is two-dimensional Toda lattice. So it can be rewritten in several different forms. So here also Q is a function of two independent variables x and y. But so this is a non-scalar case. So we have in general we can have infinite number of variables, and so they are the neighboring variables are related by such an equation. So this is a two-dimensional generalization of the Toda chain. So here I make difference. So I call the one-dimensional system the Toda chain, and the two-dimensional system the Toda lattice, in order to specify the difference. So the funny thing is that the one-dimensional system was first considered by Toda in 1967, and after that, so this system was named was named after this Toda. But in fact, and after that, people started to consider its two-dimensional generalization in the theory of integrable systems. But sometime later, it appeared that these equations, these hyperbolic equations, could be found in the book by Darboux that was written in the book by Darboux on theory of surfaces that was written in the 19th century. So this is rather interesting system because it plays an important role in classical differential geometry, and at the same time it also plays an important role in mathematical physics. Okay, so this system can be rewritten in several different forms, and I'm going to look at this particular form of this equation, and then I'm going to talk about its discrete versions. Okay, so this was an infinite system, and the natural question is how to get a finite system. So in theory, we can consider different closures, different boundary conditions of the system. For example, we can consider trivial boundary conditions. So in this variable, we just need to set the boundary functions to be equal to minus infinity, or we can consider periodic boundary conditions as well. And but these boundary conditions are particular cases of the so-called exponential system. So here the superscripts are they just number the functions, and a's are constants. So I'm going to consider the systems of this kind, and the system that was on the previous slide is a particular case of such a system. And so this class of systems was introduced by Alexei Shabat and Ravil Yemilov in 1981. And so the natural question is, what exponential systems are integrable? Okay, so let us look at the system, and if we write down the coefficients of the equation from the previous slide into the matrix, so we can we'll get such matrix for the case of the trivial boundary conditions. And so it is so one can notice that this matrix is just the Cartan matrix of A series Lie algebras. So the simplest particular case of this system is just the Liouville equation, which was on my first slide. Yes, so it corresponds to the case when the size of this matrix is 1. And so the theorem that was proved by Shabat and Yemilov is that exponential systems corresponding to all classical series of Lie algebras, or to Cartan matrices of all classical series of Lie algebras are Darboux integrable. So I'll explain what does this kind of integrability mean in a couple of minutes. But so the message is that these systems they generalize the Liouville equation in some sense. Okay, so now I'm going to define the notion of Darboux integrability. So here we need a definition of essential independence of the integral. So here I also consider the function I1, I2, etc., ik that are y integrals of the system, and so they are called essentially independent if the rank of some Jacobi-like matrix is maximal. So what does this mean? That we differentiate all the integrals with respect to the x derivatives of these functions u of the highest possible order. So the integral is said to have order d if d is the maximal order of the derivative that is included into the expression for this integral. And so hyperbolic system of this kind is called Darboux integrable if it admits complete families of essentially independent integrals in both directions, so in the direction of the variable x and in the direction of the variable y. Okay, so this is Darboux integrability, and in the case of one equation, we only need to have one x integral and one y integral, and so that's why the Liouville integral, the Liouville equation is Darboux integrable, just because it admits one x integral and one y integral. Okay, so and now I'm interested in the problem of discretization of these systems. So how to discretize exponential systems, preserving their integrability. So the first step that was probably the first step that was done in this direction was done by Adler and Startsev in 1999. So they have considered discrete versions of the Liouville equation. So now I do not have enough time in order to explain why these particular equations are called discrete versions of the Liouville equation, but so they inherit all the important properties of this equation. Here I just wrote the formulas, the explicit formulas for n integral and for x integral. So n integral is the function that that does not change if we change n in some sense, yes. So, or this is just the function that is in the kernel of such an operator where t is the shift in this discrete direction. Yes. So okay. This is the semi-discrete version of this equation, and besides this, it is also possible to consider purely discrete version. So here u is the function of two discrete variables n and m, So actually this function is defined on the lattice, and it is also Darboux integrable in this sense. So it admits two integrals, one in the direction n and another in the direction n. And so in both cases, some specific properties of the A series Toda lattice were taken as the basis for this discretization. So the natural question is how to discretize the exponential system in general. So if we consider arbitrary matrix, arbitrary constant matrix, and write down the system that corresponds to such matrix, how to discretize this system. And so the systematic I need to say a few more words. So before I introduce the systematic approach, so here I also consider one example. Yes, and so the idea proposed by Khabibulin is to look for discretization of this exponential system in such a form. So we just here we have just some discrete analog of the differentiation with respect to y. Yes, and his idea was to look for the system of such kind that has the same characteristic integrals as the original system. Yes, so that's why I call this integral preserving discretization. So we take the system having some characteristic integrals, and then we are looking for discrete version that has the same integrals in y direction. And so here we have an example how this works for the Liouville equation. So here is another version of another discrete version of the Liouville equation, same discrete version, and it is not difficult to check that the function of this kind is an n integral of this equation. So, and this function is given exactly by the same expression that the integral, the characteristic integral for the continuous version of the Liouville equation. Okay, and so the miracle is that if we consider such an equation, that this equation also admits characteristic integral in the second direction. So this is the miracle, because it just by construction it has one integral in the y direction, in the n direction. But the miracle is that it also has characteristic integral in the second direction. Okay, and so now I'm moving to the case of exponential systems. And so Khabibulin's idea was to consider such system as a semi-discrete analog of exponential system. So what do we do here? We take the matrix M from the continuous case, then we represent it as the sum of two matrices, one of which is upper triangular and the other is lower triangular, and such that the diagonal elements of both matrices are the same, and so they are equal to 1/2 of the diagonal elements of the initial matrix. Okay, and so this is the way how I'm going to discretize the this system. So this is just the formula, and you see that here. So this is the function of this is the equation of the form that was on the previous slide, and in some sense it looks more or less similar to its continuous analog. So what is known about these systems? That so Habibulin and his colleagues, they proved that such approach provides Darboux integrable systems for all Cartan matrices of order 2. Then I proved that this approach provides Darboux integrable systems for A and C series, for the matrices of A and C series of any order. So these systems are Darboux integrable, but this method is the method I used in 2015 is not applicable to the general case. So it is not possible to prove integrability of the systems that correspond, for example, to the B and D series using this method. And so now my result is that exponential system is Darboux integrable, so that if an exponential system is Darboux integrable in the continuous case, then its integral preserving discretization is also Darboux integrable. So this is the general statement, and so I have some time left, so I have an opportunity to say a few words about the mathematics that is behind this result. So the most important guy here is the complete Bell polynomial. So what is complete Bell polynomial? So let us take the function u that depends on x, and if we differentiate it with respect to x, so I introduce these variables, and so Bell polynomial is the polynomial of this form. So we differentiate the exponent with respect to x, and then we multiply by e to the power minus u in order to kill the exponent itself, and so we get the polynomial in the variables u1, u2, etc., un. And so there is a very simple but very important property of Bell polynomials is that they satisfy such recurrence relation. And so the integrability of Toda lattices in some sense is based on this property. Okay, then just so probably I'll skip some details maybe. So these are some notions that so some notation that, so I just denote the right hand side by of the system by W, and so this is the explicit form of the semi-discrete Toda lattices. And so the thing that I will need on the next slide is that so if we consider some function f of continuous variables, so so how to discretize in some sense this the integrals. So I just substitute here the function that depend on discrete variable, yes, and so this is called fn, and this is called f sub n plus 1, where I substitute the shifted variable here. And so how do I prove that? How do I prove the existence of y integrals for this system in general? So it is possible to prove that the difference of these two, of the difference of the values of the function I at the points m and n plus 1 can be rewritten in such a form where some differential operators are applied to the integral, and so it is possible to show that these differential operators vanish on the integrals, and that's why the whole expression is 0, and therefore this difference is 0. That's why the function I is an integral of the discrete system. So I take the integral of the continuous system, and I proved that this function is the integral of the semi-discrete system. So this is how we can prove, how we can construct the how we can construct 1/2 of the integrals we need. So because this, because here we construct y integrals. But besides y integrals, we also need integrals in the other direction. And so this is, but we do not construct them explicitly, we just prove the existence. So here we use the tool that is called characteristic algebra or characteristic Lie algebra. So this is the notion that was introduced maybe by Gibber, by Alexei Shabat, and probably in some sense by Gursas. So some ideas of this kind could be found in one of the papers by Gursas. So what is a characteristic Lie algebra? So it is generated by operators of such form. So these are, so here we have Bell polynomials of some linear combinations of our variables, and so the Lie algebra generated by these operators is called the characteristic algebra of an exponential system. And so there are two important facts about the characteristic algebra. The first one is that any y integral of the system annihilates the whole characteristic algebra, so all of these operators vanish on each of the y integrals. And besides this, exponential system is Darboux integrable if and only if its characteristic algebra is finite dimensional. And so this provides a tool to prove Darboux integrability of our system. And so I just proved that characteristic algebra of this semi-discrete analog of exponential system is isomorphic to characteristic algebra of the initial system. So, so this means that if the initial characteristic algebra is finite dimensional, just because we know that continuous systems are Darboux integrable, this means that our characteristic algebra of the semi-discrete system is also finite dimensional, and that's why the complete family of Darboux characteristic integrals exist. Okay, so I think I should stop here just because I do not have more time.
And unfortunately, we have no time for the but may I remind you that after the last talk at 5:30 Moscow time, some time is reserved for any kind of discussions. So our next speaker is Alexander Tumanov. Sasha, are you here? I have seen you.
Hello, do you hear me?
Sasha Tumanov, yes, we hear you, and perhaps we will see you in a while I introduce you. So we'll hear now a talk of another friend from the student times. He is perhaps the only participant of this conference of the same age than I am. Perhaps the speaker can also be congratulated with the same event in his life. We were also co-authoring some papers, and perhaps the speaker will or will not mention it in his talk. Okay, please, Sash.
Oh, thank you. I am happy to speak at the conference in honor of George Shabat, my old friend Yura, on the occasion of his 70th birthday. I wish Yura good health, happiness, good students, and good new research accomplishments for years to come. As Yura said, we met at the university. We studied together, and we've been friends since then. We had a good time. We talked about mathematics, singing songs with the guitar at gatherings. Yura was a source of inspiration for me as a hard-working person. He had the ability to and energy to work on in different occupations. He was simultaneously a mathematician, a programmer, a teacher, and a tutor. And he managed to do all these things with a passion. In spite of different research interests, we managed to collaborate at some point. Yura suggested a problem and method for solving this problem, and we wrote a paper together. We proved that every linear group can be realized as a group of all holomorphic automorphism of a bounded domain in complex space. That is, in some sense, we confirmed that the set of holomorphic automorphisms is large. My topic today is opposite in some sense. The goal is to show that they're not too large, and in fact, in some situations are determined by only a few parameters. Okay, let me put my notes on the screen. Okay, the title is Finite Jet Determination for CR mappings. What is a CR mapping? It is a diffeomorphism between two real manifolds in complex space that satisfy tangential Cauchy-Riemann equations. So the problem of finite jet determination is that every such map is uniquely defined, uniquely determined by its finite jet at a point. This problem has been popular since a very long time, 50 years ago, and the number of publications is indeed enormous. Nevertheless, some natural questions remained open, and I will discuss this. So this is a short plan of the talk. So I recall what CR manifolds and mappings are, conditions on them, and so on. So let F be a smooth real submanifold in complex space. Important is complex tangent space, which is maximum complex space contained in tangent space. So dimension of complex tangent space is called CR dimension, and CR manifold is a manifold so that CR dimension is constant, doesn't depend on the point. We consider generic manifolds means that tangent space span the whole space over tangent space is a real space and it spans the whole space over complex numbers. For a generic manifold, CR dimension of complex tangent space, and real codimension, the sum of them is the dimension of the ambient space. For instance, all real hypersurfaces are generic. What is a CR mapping? CR mapping is a smooth, well, at least C1 smooth map that whose differential is complex linear on complex tangent space. So this is also called tangential Cauchy-Riemann equation. That this map is linear. It is a form of Cauchy-Riemann equation. So we will consider CR mappings, which are CR diffeomorphism. Okay, if there is a CR diffeomorphism, then the M1 and between M1 and M2, then they have the same dimension and CR dimension. We consider equations of CR manifold. So locally, CR manifold, generic manifold can be defined by equation like this. We split coordinates into two groups. So at 0, Z is the Z is the coordinate along the complex tangent space, and so the tangent space has the equation V equals 0, and complex tangent space has the equation W equals 0. Okay, so H is a defining function which has a which vanishes with first derivatives at 0. Furthermore, it's easy to see that defining function can be represented in this form. So capital F is a vector valued Hermitian form, and the rest is the error term of the third order. Okay, so F is a vector of Hermitian forms. So the number of the equation of these are real equations. The number of this equation is K, codimension of the manifold, and A's are Hermitian matrices, the matrices of these Hermitian forms. They can be regarded as components of the Levy form. Okay, but we don't need a coordinate-free definition of Levy form in this talk. So I describe some conditions on the Levy form of the manifold. So we say it is non-degenerate at 0 if these matrices A, J's are linearly independent. And moreover, second condition, that it is the form capital F is algebraically non-degenerate, means that if it is 0 for all z's, then it implies that the other argument zeta is equal to 0. In the matter of finite jet determination, this condition cannot be dropped, because if it is not fulfilled, then the quadratic manifold, just the quadric in which the equation consists just of the Hermitian form F, this has infinite dimensional set of CR maps to itself. So in this case, without this condition, finite jet determination cannot take place. We say that M is strongly non-degenerate if it is non-degenerate. In addition, there is a linear combination of matrices A, which is non-singular. And finally, we say that M is strongly pseudo-convex if it is non-degenerate, and in addition, linear combination of this Hermitian form is positive definite. The problem of finite jet determination, whether the CR map can be uniquely determined by its finite jet at a point, has been a subject of work of very many authors. I list, well, some of them, and of course all of them students. So indeed the number of publications is large. We restrict to Levy non-degenerate CR manifolds. There are sophisticated results on the matter, but still, even for Levy non-degenerate manifolds, there are important open questions. Let me describe some known results. Belashapka in 1988 proved that real analytic CR automorphism or real analytic non-degenerate CR manifold determined by its finite jet at a point. So he proved finite jet determination in non-degenerate real analytic case. Much more recent result, these authors, Bertrand, Blaxenti, and Milan, proved second jet determination for smooth, in the smooth case, for some additional condition they called D non-degenerate. In particular, this implies that there exists a vector, so that the vectors A, J, Z, so the K vectors, are linearly independent over R. This condition is quite restrictive. In particular, it implies that codimension is less than 2 times CR dimensions of M. Okay, so Z is the dimension of Z is CR dimension of M, whereas the dimension of the space of all Hermitian forms on CM is M squared. So the codimension of non-degenerate CR manifold can be up to M squared. So this condition is quite restrictive. I proved 2-jet determination in smooth case for strongly pseudo-convex manifolds. This is a the set of strongly pseudo-convex manifolds is an open set in the it's open condition, but it misses lots of cases when it is not strongly pseudoconvex. So these results were obtained using an invariant of CR automorphisms, so-called stationary disks, but I will not speak about them. Use different methods today. Beloshapka very recently proved 2-jet determination in codimension 3 in real analytic case. And it was believed for a long time that 2-jet determination takes place for all non-degenerate CR manifolds, but it turns out to be wrong. So quite recently, Milan constructed a counterexample of a quadric for which 2-jet determination fails. So then, obviously, there is an important question whether to find a good condition or maybe necessary and good, necessary and sufficient condition when for 2-jet determination. So this example, Milan and Grigorovich extended this counterexample so that for some large p-jet determination fails in some high dimension. I present a sufficient condition for 2-jet determination that implies all affirmative results on 2-jet determination mentioned above, that is for strictly pseudoconvex, degenerate and codimension 3. So the approach is based on infinitesimal automorphism. So it is different from all the methods that used here that I mentioned. What is an infinitesimal automorphism? Well, it is, of course, a vector field that generates a local one-parameter group of CR mappings. So we consider non-degenerate quadric. So for general manifolds, we will only use infinitesimal automorphisms of quadrics. So we recall quadric is defined by a vector value determination form like this. And let G be a group of all CR mappings of this manifold. Then it is well known that G is a finite dimensional Lie group, and its Lie algebra is the set of infinitesimal automorphisms. And this is indeed finite dimensional, and the dimension has an estimate that depends on CR dimension and codimension. It turns out that all elements of group and algebra are respectively rational and polynomial. Particularly, every vector field in the Lie algebra has, well, we use this notation, Fg, denoted by F and G, Z and W components, respectively. So for their polynomials, if X is an element of Lie algebra, then it's polynomial and satisfy this equation. So F and G satisfy this equation when Z and W on the manifold. Okay. It's important that this Lie algebra has a natural grading. So if we give the variables and differentiation weights, so z variable have weight 1 and w variable have weight 2, and then differentiation -1 and -2, then it turns out that this grading of the polynomials agrees with this with the structure of infinitesimal automorphism. So the algebra of infinitesimal automorphism actually is a natural graded Lie algebra. The grading starts from -2 and goes all the way. Well, then actually it's finite, but it can be, as we know by these counterexamples, this can be large. So the terms g-2 and g-1 have a common description for all, no matter what quadric is. This terms g-1 and g-2 is sometimes called a group of parallel displacement. The groups, this group acts freely transitively on M. And the whole group of the whole algebra of infinitesimal automorphism, it is in some sense the maximum Lie algebra that is determined by g-1 and g-2, so that each term, each member of P's component is uniquely determined by its adjoint representation on G1. Okay, so it turns out that finite jet determination of CR maps follows from finite dimensionality of infinitesimal automorphisms of the quadric. Okay, so we have the following result: if the component GP, if you have two smooth non-degenerate CR manifolds defined by equations as above, if suppose that P component for some P, GP is equal to 0, then every germ at 0 of a smooth CR diffeomorphism M to M prime mapping 0 to 0 is uniquely determined by the jets of F and G at 0 of weights respectively P and P plus 1. And for P equals 3, when G3 is equal to 0, it implies a second jet determination for CR mappings. My contribution here is the so Beloshevko proved the theorem for this theorem in real analytic case and long ago. And my, well, say, small contribution consists of extending this to the smooth case that has been an open problem for a very long time. So I don't have time for the proof. The idea goes back to Poincaré and Cartan, that we just have the weighted Taylor series of all this stuff, and when plug everything in together, then it turns out that components of p-weighted components satisfy equation that is equation for infinitesimal automorphism of quadrics, turns out. So, and then we can gradually determine all the Taylor coefficients. So this completes the proof in real analytic case. In the smooth case, actually we can consider this at all points, and this results in a partial differential equations. And this is very overdetermined equations, and whose solutions is uniquely determined by a jet at just one point. A couple of words for second jet determination. For hypersurfaces, it was proved by Chen and Moser in 1974, and then in 1967, many cases were proved by Tanaka. He proved that G3 is equal to 0, but his conditions were very restrictive. Then, as I told earlier, that there was a condition D non-degenerate, which was also quite restrictive. And Bertrand and Milan proved two-jet determination under this condition. I state my condition for second jet determination. For every set S, we define orthogonal complement with respect to vector Hermitian form in this way. And then we also determine the space T of Z consists of all P such that there exists Q, so that this sum is equal to 0, which reminds that we just differentiate this Hermitian form with respect to a parameter. So when we say that M and capital F are T non-degenerate if orthogonal complement of TZ is equal to 0. This condition is very easy to check. So even easier than D non-degeneracy. And then the main result is that this is a sufficient condition for second jet determination. Well, I don't have time for proof, then I just wanted to point out that this was most general condition that covers all conditions obtained so far. And in the end, I wanted to just show the examples, a couple examples. This is example by Milan. So what kind of example? It's Hermitian form consists of 5 components, so that, and there are 4 variables Z, and in 2 variables Z1 and Z2, we have the first, this 4 F1 to F3 are all linearly independent, well, the basis of Hermitian forms. And the 5th form is the duality between variables Z1, Z2 and Z3, Z4. And turns out this is an example in which the graded components G3 is not equal to 0, and even G4 is not equal to 0. Then, of course, in this example, it's not T not degenerate, of course, so this space is not 0. And if you consider this, in this example, only 3 components of this 5 forms, then it turns out that this is T non-degenerate, so 2J determination takes place, but this example is not D non-degenerate. Finally, unfortunately, I have to make another example that, again, based on example of Milan, I throw away only 1 component, and then this turns out to be not T non-degenerate, but one can see just directly that G3 is equal to 0. So T non-degeneracy, unfortunately, is not necessary for 2J determination. So it is still a good question to find a good sufficient and necessary condition for 2J determination. Okay, that's it. Thank you very much. And happy birthday to Yura again.
Thank you. Any very short questions, please? Well, maybe I have one. Shura, can you formulate in non-technical terms what you said at the beginning, that your results show under some assumptions that the amount of automorphisms is small?
I just mean that well, 2J determination means that the CR map is determined by just finitely many parameters. Okay, so usually generically, if you take this CR manifold at random, that there will be no CR automorphism. So that the question, it's important question to know, to find CR manifolds with rich group of automorphism, and they are quadrics. In fact, for a general CR automorphism, the most mappings there are from quadrics. Okay, so and then there are some good examples that involve, say, classical domains, Siegel domains. The Shilov boundary of a Siegel domain is a strongly pseudo-convex CR manifold. Then they may have a rich group of CR automorphisms, but in any case they are determined by finite jet, and say for strongly pseudo-convex and as the main topic of this is T non-degenerate, they are uniquely determined by second jets.
Now let's thank the speaker again. We are a bit in retard, but it's not so dangerous since we are approaching the end. Dimitri Zvonkine, are you here?
Yes.
So I'm happy to invite Dima, whom I know from just his very young age as a very bright person interested in mathematics. Now, during these decades, this interest flowered in
very fruitful directions, as I think we'll see immediately.
Thank you very much. So happy birthday. I'm joining you from a physics conference because for the first time in my life, I'm going to talk about a physical problem. So it is a joint work with Semyon Klevtsov. Maybe I'll write that down. So what happened is that we used some serious algebraic geometry, more precisely the Grothendieck-Riemann-Roch formula, to solve a question in more or less concrete physics in quantum Hall effect. Quantum Hall effect. So what is the Hall effect? It's really a concrete physical experiment that was first conducted in the 19th century. So you take a conducting plate, a thin conducting plate, and it is traversed with a strong magnetic field. So usually people draw something like that as an arrow that crosses the plane of the blackboard, of the whiteboard. And then there is a measuring device connecting the left side with the right side, and there is something it can measure, maybe the voltage or the current, or maybe it contains a battery and can inject some voltage or inject some current. And same thing, there's another measuring device that connects the upper half and the lower half. So if you look at photos of experiments, you can actually see many electric wires going as in my picture. And so what happens in the Hall effect is that when you have a voltage that pushes the particles along the x-axis from left to right, because of the magnetic fields, they start to deviate and turn. And instead of getting the current just along the x-axis, you also get a current along the y-axis. So there is something called Hall conductance. Maybe I'll write it here before going to the next page. Hall conductance. It is the current along the y-axis divided by the voltage along the x-axis. So there's the usual conductance along the x-axis, the current divided by the voltage, but there is also a perpendicular current. And then the quantum Hall effect occurs when you cool this setup to some low temperature. And then it reaches a very surprising regime where you apply the voltage from left to right, and you do not get any current from left to right at all. You only get current from in the y direction. So the current is perpendicular to the voltage. Of course, an unusual quantum effect, somewhat similar to the superconductance, where you see a macroscopic quantum effect in a more or less large-scale experiment. And so the question is, the problem is to explain how this happens and see if we can compute theoretically the Hall conductance. And there are different other questions. So when you see this picture of a rectangle with upper side identified with lower side and left side identified with the right side, of course, all Shabat students know it is a torus. So as a good mathematician, I just draw a surface, and we will study the quantum Hall effect on the surface. So actually in experiments, nobody went beyond genus 1, the picture that I showed you above, but normally it should be possible to create an octagon and connect sides with wires in this way. And again, we all know that this creates a genus 2 surface. So normally it should be possible to make an actual experiment in genus 2 using an octagon. Okay. So what is the what is the plan for the next 20 minutes?
Well, they can be extended a bit if you need.
Yura, was that for me or not?
Yes, you can extend your time a bit.
You can okay. Well, we'll see.
Penultimate.
Okay, we'll see. Sorry. So the plan is to give an introduction to electromagnetism in this particular case, and notice that rather miraculously all the questions, all the important features happen to depend only on the structure of the Riemann surface. So this is a physical surface, or maybe this physical surface. So it has a Riemannian metric. Riemannian metric, just because it is a physical object, so it's a manifold in 3D. And the Riemannian metric, it can be decomposed as a complex structure and a symplectic form. So I think it is rather well known that when you have a Riemannian metric, you can at every point you can measure you can define multiplication by I, which is just the rotation by 90 degrees. So this will give you the complex structure. I is the rotation. Rotation by 90 degrees. And then different metrics, if two different metrics determine the same rotation, the same complex structure, that means that they differ by multiplying by a positive function. So there is also the symplectic structure that gives you a measure of area, and both together are equivalent to a Riemannian metric. And we will see that rather magically, all the relevant features only depend on I and do not depend on the symplectic structure. And because of this, it's a problem about Riemann surfaces, algebraic curves that can be solved by algebraic geometry. So let's look at one particle. One particle in an electromagnetic field on a surface. So here is our surface again. Maybe I'll draw it in this way, because this is our space and we also have time. So this is our space-time, C times R. And so for those of you who ever followed courses in electromagnetism, it's a gauge theory. The electromagnetic field is defined in the following way. So we have a U1 bundle, let's say P over the space-time. That's a U1 bundle or a circle bundle. circle bundle with a connection nabla. And okay, and the curvature of this connection is the electromagnetic field. So this is the standard way to introduce the electromagnetic field. So since it's the connection on space-time, its curvature. So the curvature is a two-form, and the two-form has a component, well, space component, that's the magnetic field, and a space-time component, and that's the electric field. So if I write nabla equals d plus alpha of, okay, so let me say, okay, I have to be careful. So you see over each point now we have a circle. Over each point here, this is just one line. This is just one timeline, but you can also take any point here. So over every point of space-time, we have a circle. And we can decide to use the parallel transport. So the connection gives us the parallel transport. In particular, it gives us a parallel transport along this timeline, so that, and I can decide to trivialize the circle bundle using this parallel transport. So it's a choice of gauge. In physics, it's called a choice of gauge. Trivialize the bundle along timelines. And that means that the connection does not have a dt component. So normally, if we have coordinates x, y here, and t is time, normally we would have, the connection would be d plus a dx plus b dy plus c dt. But by choosing this gauge, I remove the last term. So the connection becomes just something like that, d plus one form on the surface. That's a one form on C. And that depends, so that depends on time, but it doesn't have a dt component. Okay, and now the magnetic field is d alpha, it's a two form. And the electric field is d alpha over dt. That's a one form. Okay. Now I start with, let's start with just B. Start with just B. So that means alpha does not change with time. I just have my surface, a circle bundle over this surface, and a connection nabla. E over C. That's a U1 bundle. Okay, so that means, well, when I have a circle bundle, I can always create a complex line bundle just by multiplying with the complex line over U1. That's a line bundle, actually a Hermitian line bundle with a connection. And if you know some analysis, I confess that I had to learn that precisely for this purpose. But actually, when you have a Hermitian line bundle with a connection, it automatically acquires a holomorphic structure. We define d bar to be the 0,1 part of the connection, and that gives a holomorphic structure. Holomorphic structure on L. So you see, just by when we just have a surface traversed by a magnetic field, that means that we have obtained a holomorphic line bundle over a Riemann surface. So our surface has a, because it is a 3D surface, it has the structure of a Riemannian manifold. In particular, it has a complex structure. And if we have a surface with a complex structure, so a Riemann surface and a line bundle with a connection, a Hermitian line bundle with a connection, it automatically becomes a holomorphic line bundle. So we have a Riemann surface with a line bundle. Okay, now the next thing is to write the Hamiltonian of one particle. Hamiltonian of one particle. And this Hamiltonian actually is d bar star, d bar plus constant. So this is the operator. Well, psi goes to this thing times psi. So if psi is a wave function, maybe I should say psi is a wave function. In this case, it is a section, an L2 section of L. So I will remove this L2 to avoid confusion, but it's not a smooth section or holomorphic section. It's the section of this Hermitian line bundle L that is of so square integrable. And this is the Hamiltonian. And so what do we see? Now, if we're looking at the lowest, at the ground state, so the ground state is the eigenfunctions of H with smallest eigenvalue. Smallest eigenvalue. And these are actually holomorphic sections of L. Because to get the smallest eigenvalue, you need this d bar of psi to be equal to 0. And ground states, so these eigenfunctions with smallest eigenvalue are precisely what we get when we use very low temperature. So when we cool our conducting plate to very low temperature, the particle freezes and settles to the state with the lowest energy. So we have already obtained something funny. That's what is called the degeneracy of the ground state. It is very funny because the precisely the same notions have completely different names in physics and in math. So the degeneracy of ground state. Well, in math, we denote that by the dimension of the space of holomorphic sections of L. And this is given by the Riemann-Roch formula, degree of L, or first Chern class of L, plus 1 minus G. And by the way, the degree of L is the total magnetic flux through C.
Dima, do we still assume that genus is 2?
No, any genus. Any genus. Okay, so now I will speed up and just explain briefly what happens next. So first of all, first thing, now we switch on the electric field. And then it gets more interesting. So now our connection can change. And as I said, a connection on a Hermitian line bundle actually gives you a holomorphic structure on this line bundle. So now the holomorphic structure on the line bundle will change. And that means we're actually traveling in a Picard group. So if let's denote the degree of my line bundle by D, then we have the Picard group, the dth Picard group of C times C. So this Picard group, so it's a G-dimensional complex, a torus of complex dimension G, and it parametrizes all degree G line bundles on the Riemann surface. And so over each point, we have a Riemann surface with the corresponding line bundle. Right, the line bundle changes from point to point. And switching on E means moving along the Picard group. So this is switching on E. The electric field makes us move along the dth Picard group of the Riemann surface. And there is even the physical terminology for the Picard group. I made this social experiment during the physical conference I am at now, that physicists do not know the words Picard group. Instead, you should call it the moduli space of Aharonov-Bohm fluxes, and then they understand. Okay, so now we get a family over the Picard group. And then there's another change that's normally, of course, there is not one particle on the surface, but many particles. So instead of just taking times C, we actually take, so still the Picard group of C, multiplied by a high symmetric power of C. Let me write a proper N. So why do we need a symmetric power? That's because the wave function of two indistinguishable particles, it's not just, so if we have two particles at points Z1 and Z2, we have a function Z1 and Z2, but it is supposed to be symmetric or anti-symmetric when you exchange Z1 and Z2. So actually, we're interested in sections of L that depend on capital N parameters if we have capital N particles, but they should be Sn invariant. So actually they are sections on this symmetric power. Okay, so two last sentences. I'm just showing you the setup. So now we have the Picard group. We have this, so I will still draw the picture with Riemann surfaces, but actually we remember that it's symmetric power and symmetric power of C. We have a line bundle over this whole picture. Let me call this projection pi. And we would like to take the direct image pi lower star of L. That is sections, so sections of this, holomorphic sections of this line bundle. As before, holomorphic sections of this line bundle are ground states. So at cold temperature, the particles freeze down to holomorphic sections of this line bundle L. And what we get is a vector bundle over big D. And then there is one last miracle that I will not have time to explain, but I formulated at least. The curve, so let me denote this V, and then the curvature of V is the whole conductance. And there is actually a proof of that that I don't find particularly simple. So it is not a simple fact. It's not just a matter of terminology. You need to actually understand how to measure current on the Riemann surface, and it's not so simple. But in the end, you find that to measure current, you measure the curvature of some particular connection on this vector bundle. So the moral of that is that physicists are actually interested in Chern classes of this vector bundle, because so a curvature is at one point, but usually when you actually measure the current, you get some kind of average, and the Chern classes give you the average over the whole Pk group. And there is the Grothendieck-Riemann-Roch formula that does precisely that calculates the Chern character of V as a push forward of the Chern character. So sorry, of the exponential of the first Chern class of this line bundle L times the Todd class of the projection pi. So it is some computation in cohomology of this d times the symmetric power of the curve. You need to understand the cohomology ring of the symmetric parts and symmetric power. So it's some computation, but it is doable, and you get an answer that to a physical problem that you can actually measure in an experiment. And I will stop here. Thank you very much.
Any short questions, please, or short remarks? Seems that none. Let's thank the speaker again. Daniil, you're here. Very good.
So thank you very much for the invitation. I'm very happy to give a talk at this birthday conference. I should say that currently I'm teaching a long course on elementary mathematics for undergraduate students. And I think there are at least 3 occasions in the course where I use the educational tricks I learned from Georgy Borisovich back in Dubna. And I think 2 tricks I already used was Möbius strip and belt and something else. And then there, at some moment, Georgy Borisovich was showing us how to think about a group of rotations and used a huge pair of sticks glued to each other. And this is yet to go, so I'm a little scared of being able to repeat this computation of fundamental group of SO3, but I will try. So today I want to talk a little bit about volumes of hyperbolic polytopes and their relation to Goncharov conjecture. So there are also cluster polylogarithms in the talk, which I can say a few words about at the end, but actually maybe that's not the focus today. Let's look at hyperbolic polytopes. So one of the most natural questions one can ask is a question of volume. So what is the volume of a polytope? And in Rn, there are many different answers, but at least we know it's a rational function of, say, squares of lengths of edges. For tetrahedra, for general polytopes, it's more complicated. But in hyperbolic space, the question is more maybe interesting because already in dimension 1, new functions arise. And the question we start maybe looking at first is what kind of functions one needs to talk about volumes. So very classical function. And if you look at dimension 1, so I just drew here a picture of a hyperbolic line, hyperbolic segment. So Q1 and Q2 are ideal points of the boundary. And I'm using Klein's model for hyperbolic distance. And then the volume between 2 points, which is the length, is 1/2 logarithm of the cross ratio. So cross ratio is a rational function of coordinates of vertices at least, but logarithm is a transcendental function. And the question is, if we go to higher dimensions, what kind of transcendental functions we need? And of course, one can say, but just volume is itself a function of coordinates of vertices of a polytope. But at the same time, it has many, many variables. And it is very tempting to try to express it through some simpler functions. So one of the first functions I want to talk about, and I will need it, is called classical polylogarism. Everything is fine? Any questions?
No. There were technical issues. They're solved.
Sorry. Okay, so classical polylogarism. And classical polylogarism is a function which will appear today a few times. And it is just a close relative of polylogarism, of logarithm. It's a power series for, in a unit disk, it's a convergent power series, which is on the board. And it was first studied by Euler, and Euler found, so it was written by, in the correspondence between Leibniz and Bernoulli, but actually the first results were by Euler. And here you can see a functional equation Euler found, which he used to efficiently compute the dilogarithm of 1, which appeared to be equal pi squared over 6. Then the function was studied further. It satisfies lots of algebraic equations. So I mean, by equations, I mean where you basically take a function and the arguments are certain rational functions in many variables. And in general, one should not expect such equations to exist. They are very special, maybe fact, property of polylogarithms that they exist. And Abel found the famous 5-term relation, which I don't write in full, but I write the kind of the main logarithmic part. And later on, Kummer worked on similar equations for Lie3. Probably, I'm not sure there was any particular application. It was just interest. And he found a few equations. He found certain equations for Lie3 and Lie4. So that was in kind of a problem which was catching some attention. And finding equations for higher polylogarithms is very hard. So Goncharov found some more general equations for Lie3, which it's open question whether it reduced to Kummer or not, and I believe not, but Goncharov believes that it does. So it's not clear. And then in 2016, Herbert Gungel found using a very involved computer-assisted techniques, computer-assisted search, a functional equation for Lie4, which is the smallest general, and it has 900 terms. So basically, classical polylogarism is a very interesting function satisfying mysterious equations. And the reason why they are so hard to find, it's not clear what kind of arguments to put in. So just some rational functions, but on what and with what properties. So this was a little discussion of classical polylogarism. Let's return to our question. So the first result on polylogarism and volumes was due to Lobachevsky. So as early as in his first work, Lobachevsky worked on computation of volumes of hyperbolic polytopes. And before the model for the geometry was all established, obviously. And he actually showed that volumes of a polytope in H3 can be expressed via dilogarithm. I mean, what I mean is you take a polytope in H3 and maybe fix that you work in Klein model and take coordinates of vertices in this Klein model, and then use the statement is that it's sum of dilogarithms of certain rational functions, maybe quadratic irrationalities in this coordinates. So that's kind of the results I mean when I say volume can be expressed. And so after that, the next progress on the question of computing volumes, it's very natural to try to do the same thing for H5, but the first progress was done more than 100 years later in the work of Bloch and Guterman, where they showed that volume of a polytope in H5 can be expressed via trilogarithm. And there they don't have a formula. It's very complicated reduction. So they kind of it's one can use it to find an algorithm, but it's pretty horrifying. And they conjectured that actually the same is true in higher dimensions as well. That just all volumes of hyperbolic polytopes can be expressed through Li-n. So let me just mention that I mean, in particular, hyperbolic polytopes, manifolds, because you can cut a manifold into hyperbolic polytopes and add their volumes. So basically, whatever question we are answering, what sort of numbers we get when we compute volumes, very important volumes of hyperbolic manifolds will be there. And also, by the way, special values of zeta functions of totally real fields will also be expressible via the same functions because they can be expressed via volumes, basically. Then Joseph Bohm disproved this conjecture. So in H7, it's not longer true, and volume of a polytope cannot be expressed via Li4. And he actually proved it. Maybe there are little details which are not clear, but he gave a proof. Later, he actually proved a very strong result. He explained that volume of arbitrary polytope can be expressed through what's called multiple polylogarithms, which we will come to a little bit later. And this result was not known for a long time, and I discovered it only recently. So in his paper, he doesn't mention it at all, and multiple polylogarithms are not defined. And actually, at that moment, probably there was not much attention to them. And what he writes instead, he writes that he has a certain integration procedure. And it's a very, very deep proof. It's not at all technical. I mean, it's technical, but it's not at all just technical. And eventually, he actually proves this theorem. But further, people who worked on the problem kind of have not maybe understood that actually it's proven. Me neither. So I didn't know about his work at all. Our goal would be actually to give a proof of a theorem of Bohm. So we will give a proof which is different from Bohm. So there are some actually deep common ground. Moreover, we will do a thing which is not done in Bohm's work at all. We will give an explicit formula for volume of an order scheme. And order scheme is a kind of a polytope, which I will talk about in a second. But it essentially gives a explicit volume formula for arbitrary polytope. So that's the goal. And in the in the last couple of minutes of the talk, I will explain what it has to do with the depth conjecture of Goncharov and multiple polylogarithm depth filtration, which was a kind of a corollary of this result and an unexpected one for me. Any questions?
No.
Good. Okay, so let's talk a little bit about order schemes. So order schemes are very classical type of polytope in higher dimensions, in any dimension. So let me start with the definition. So you take a collection of hyperplanes in any space, hyperbolic, real, or spherical, does not matter. And then you require that faces hi and j are orthogonal for I minus j being bigger than 1. So that's a little hard maybe to grasp from this formulation, but let me just draw some pictures. So in dimension 1, there is nothing to require. It's a segment. And in dimension 2, that's just a right angle triangle because you have 3 faces and you want the first and third to be orthogonal. So in dimension 3, that's a polytope which is obtained by taking a segment A1, A2, going perpendicular to it via segment A2, A3, and then going perpendicular to the whole plane by segment A3, A4. So basically you take a tree of segments and embed them pairwise orthogonally into your space. And what is interesting about order schemes, so order schemes were introduced by Schlafly back in the first book, where he also talked about polytopes, Euler characteristic of polytopes, and metric on Rn, and so on and so forth. It's all in the same paper, and he in quite detail studied order schemes there. And so what is interesting about order schemes for us is that order schemes have a property that faces and angles, if one is careful, of order schemes are as well order schemes. So they are closed under passing to the boundary. You get right angle triangles as four faces of the polytope in the picture. And actually one can easily show that that's the only family of polytopes with these properties. So if you have a polytope whose all two-dimensional faces are right angle triangles, it's already an order scheme. And if you have a simplex, sorry. And so what makes them so interesting is that, so they are higher dimensional generalization of order schemes. And basically, of right angle triangles. And basically, what I'm going to talk about before computing their volume, I will explain a little bit of trigonometry of them, which you can think of a very wide generalization of Pythagorean theorem. That's kind of there is a way to understand trigonometry very well. And it's due to Coxter. So, by the way, let me just make a remark that for those who are familiar with Caesar congruence and Den invariant, so a Den invariant of order schemes can be expressed through order schemes. So in the Hopf algebra of Caesar congruence classes of polytopes, order schemes form a basically sub-Hopf algebra. And that maybe makes them very suitable for studying in this regard. So, and also I said that any polytope is Caesar congruent to union of order schemes. That's really easy. Just statements that you can cut a polytope into order schemes. And for this, you just take any point inside and start projecting heights. And using heights, consequently, one can get sort of a barycentric, orthogonal barycentric subdivision, and that will give a decomposition. So let's move on. So let me start with a formula of Lobachevsky, which is pretty complicated, but also beautiful. So he computed a volume of an order scheme, and this is the same scheme as before with three angles, alpha, beta, and gamma. And he computed a volume of an order scheme, and he introduced an extra angle delta, which is very hard to visualize what it is, and it's given by some algebraic expression, where on top you can see the square root of Gram determinant, which is fine, but other than that, it does not make much geometric sense to me. And then using this extra angle delta, one can write down a rather pretty formula for volume. So you can see there is 1/2 imaginary part, which is not that important. And then it's just sum of dilogarithms where you plug in exponents of these differences and sums of the angles. And the reason why this formula is so complicated is exactly that this angle delta is kind of strange. So it's not, if it were just angles of an order scheme, it means the formula is very simple, but no, it has this angle delta, which is of unclear geometric meaning. So he obtained it by direct integration, basically. And since every polytope can be cut into order schemes and every order scheme's volume can be computed by this formula, it means you can express any volume via dilogarism. And so now let me pass to the statement of a formula for volume of an order scheme, and then we will discuss applications. Any questions at this moment?
No, please proceed.
Okay. So first, we need the supply of functions to use in the formula. And I mentioned classical polylogarithms, but I also said that they're not sufficient. So we need something extra. So we will work with multiple polylogarithms, which are multi-valued functions depending on integer parameters. And they're also given by certain nice convergent power series. So for some, there are values at 1 might be more familiar, which are known as multiple zeta values, MZVs. And also I should say that multiple polylogarithms are the same thing as iterated integrals on projective line. And so they were studied in various ways by Poincaré and many other people. So they are very actively studied and in a sense simplest function of their type with unipotent monodromy probably. And so so this is the supply of functions. So the number n is called the weight and the number k is called the depth. So I don't want to get here in the theory of motives, but actually one can say, so they underline variations of mixed Hodge structures of mixed state type. So it means mixed Hodge structure where the Deligne-Betti numbers are 0, except for the case when they are on the middle strip, like B equal to Q. And conjecturally, that's conjecture, universality conjecture of Goncharov says that all periods of mixed state motives are expressible via these functions. Underlying idea of the whole maybe approach to volumes is that volumes of hyperbolic manifolds and polytopes are periods of mixed state motives, as Goncharov shown. So it is kind of what we are trying to do is a special case of this universality conjecture, which is widely open in general. But it's a non-trivial case. Or maybe first non-trivial case, or one of the first non-trivial cases. Let me just say, so k is called depth, and this is a mysterious parameter we'll talk about later. And just for visualization, I added polylogarithms of different depths, which have weight 4. So here is the whole list. And only the depth 1 case is a classical for logarithm we kind of started with. So now we have this functions, and we want to express volume of an order scheme via them. So how to do that? So first, we want to make a problem a little bit more algebra geometric, and we define projective order scheme to be a configuration of a smooth quadric in projective space and a collection of hyperplanes with the same orthogonality condition. So that's actually the same thing if you use Klein's model for hyperbolic geometry. I draw a picture of a disk. So in hyperbolic, if you want to draw a hyperbolic circle in Klein's model, it will be a conic, which might be taken as a circle, and a triple of lines where now 2 of them are perpendicular with respect to a conic. And so this gives me a way to deal with polytopes which are kind of obtained from hyperbolic by analytical continuation. So it's very natural. And then, yeah, so every hyperbolic order scheme is such by taking as a quadric the projectivization of the boundary, and from faces projectivization of faces. So now I want to state a theorem, which is maybe one of the key points, and it's an elementary theorem, but unfortunately I don't have time to prove it. So it's a theorem which is essentially due to Coxeter, who proved it for hyperbolic case, prove at least some statements here for hyperbolic and Euclidean and spherical case. So the statement I give is a little bit more general, and also a proof which I'm not going to give, but I can say just a few words is new. So the theorem is absolutely remarkable. So it tells that there exists a bijection between generic projective order schemes and configurations of points in P1. So I guess that among the audience of the talk, there are many people who worked with configuration space of points, like moduli space of stable rational curves and so on. So basically, that's another interpretation. And one can ask, but of course, I mean, both are rational varieties. Maybe it's not that surprising there in bijection, but actually the remarkable part is that if you look at faces and angles of an order scheme, they will correspond to subconfiguration. So basically, forgetful functor on configurations results in passing to angle or edge of an order scheme, or higher dimensional version of that. So somehow the theorem was missed by the community. I don't think there are any references on it, though it precedes just one of the very famous papers of Coxeter about Friezes. which people in cluster algebra community looked at very carefully. And I think that this was a motivation for Friezes, because Friezes is a study of configuration space of n plus 2 points and cluster structures there, basically, in some version. And this was just after this. So let's look at the theorem. So for n dimension 1, both order schemes are just segments, hyperbolic segments, parameterized by their lengths, and 4 points on P1 are parameterized by cross ratio. So I can do any correspondence, and one can naively take logarithm of cross ratio as a identification, and that's not what I'm going to do. So I'm going to do this weird function. I say that cross ratio is equal to minus hyperbolic tangent square of the length of the edge. So that looks completely bizarre, but in dimension 1, I'm allowed to do anything. And then if one looks at dimension 2 case, then actually everything is fixed, because in dimension 2, we have a right angle triangle, which has 5 parameters being 3 lengths of edges and 2 angles. And I said that passing to angular edge corresponds to forgetting point. So it means there should exist a tuple of 5 points where cross ratios give me angles and edges via the same formula. And that's a famous pentagram mirificum of Gauss. So I formulated in the spherical case, though it's true also in hyperbolic case, if one takes a triangle with angles alpha, gamma, and sides ABC, then there exists a configuration of 5 points, so that the cross ratio are tangent squares of angles or this pi over 2 minus, I mean, angle, like tangent squares or cotangent squares are angles or edges. So this is a result of Gauss, and the theorem of Coxeter is a higher dimensional generalization. So for 3-dimensional order scheme, we will have 6 points. And let me just say, so there is a very elementary construction based on Kashivara's version of algebraic Maslov index, which I'm not going to say, but it would take like 10 minutes to explain. Let me skip it, but one can do. Any questions about the theorem of Coxeter? Okay, so at this moment one can start wondering. So volume of a polytope is known to be some kind of iterated integral, and we just said that order schemes are parameterized by points of P1, and so it means that probably volumes should be iterated integrals on the moduli space of points. And such iterated integrals are very well understood thanks to Arnold's formality theorem for cohomology of the moduli space. And so something interesting is going on here. So this is not true what I said. I mean, the reason being that actually volume of an order scheme is defined not on this M0n space, but on its covering. So one needs to take a finite covering of M0n where square roots of cross ratios are well defined. Well, abstractly, this is a sort of it's called level 4 subgroup of the spherical braid group, and one needs to pass to a covering corresponding to this subgroup of the spherical braid group, which is pi 1 of the M0n. And on this finite, so why one needs to do that? Because actually volume is defined only there. Because to compute volume, one needs to choose a certain value of a square root of Gram determinant, basically, and it appeared to be related to square root of cross ratios. And so this variety, as this M0 2n plus 2s, is not rational anymore for maybe n greater than 3, and or even maybe n equal to 2 already. I'm not sure. I think n greater than the n equal to 2, it's already not rational. So one cannot apply any simple results to express volume via iterated integrals. So it's kind of a miracle that this function expresses. So let me finally give the formula. So we take a 2n plus 2 gon, and we think of vertices of this polygon as points in P1, and thus corresponding to an order scheme. So an order scheme is parameterized by this kind of polygons with points x0, x1, and so on, labeling the vertices. Polygon is combinatorial object here; it's not geometric. And then let's denote by Q the set of quadrangulations. So that's a kind of a fun notion of a quadrangulation. You just cut a polygon into fourgons, and the number of quadrangulations is given by a kind of a generalized Catalan formula invented by a student of Euler. So then every quadrangulation defines for us a dual tree, and actually it's a rooted tree. I will take a root to be adjacent to the quadrangle having 0, 2, and plus 1 as a side. And now I need to write down a formula. So what I do now, let's suppose I have a rooted tree labeled by certain complex numbers, and then I can compute multiple polylogarithms attached to this rooted tree. So it's a slight generalization of just multiple polylogarithms. If my tree is just a segment, it will be just multiple polylogarithms of the corresponding numbers. And I have this little m, this is kind of extra depth I add, which is not, I mean, I can do that. And in general, the formula is that you take multiple polylogarithms over all permutations of elements labeled, which are labels of the vertices of a tree, but you take permutations which are consistent with the ordering defined by a tree. So you want to permute things so that the ordering will be consistent with the partial ordering defined by a tree. And then there are some lower depth corrections, which I'm not going to say, but one can understand their structure using Kohn-Kreimer-Hopf algebra of trees. So there is some way to write down a formula. And after one does that, one can write down a formula for volume of an order scheme. So this is it. We take 2n plus 2 gon with vertices labeled by points, and we take any quadrangulation, a tree, and label the tree by square roots of cross ratios. And then we just sum over all quadrangulations, and we sum over all signs of square roots with a character. So signs, if square roots changes sign, we change the sign before the value. And that gives the volume as a multi-valued function. One can get it a single valued as well, but let me not go into it. Just an example is that if you take the case of 6 points, you will get a formula which one can very easily show is equivalent to a formula of Lobachevsky. So there are 12 terms here, sorry, 4 times 12 terms here, which correspond to 3 quadrangulations of a 6 gon, and all 4 choices of signs before the square roots of cross ratios. And that is equivalent to the formula of Lobachevsky. So this proves the theorem of Bohm and gives this kind of formula. So let me just say one word how one proves it. So one needs to use this coproduct Hopf algebra of Caesar congruence of polytopes, and coproduct being then invariant. And basically, there is a way to extend it to multiple polylogarithms, and this uses a theory of mixed Hodge structures. And then one can compare coproducts on left and right hand side, and there is a kind of algebraic, combinatorial algebraic argument explaining why in the right hand side all the complicated terms cancel and the simple terms give you just left hand side. So this I'm not going into at all, but there is a way to do that. Okay, so this finishes the story of volumes of polytopes, and I have in mind giving an application to depths of polylogarithms. Do I have time for that? So depth conjecture. So the question is when a sum of weight and polylogarithm can be expressed via polylogarithms of depths less than d. So when one can reduce the depths of a certain combination of polylogarithms. And in weight 2, that's always true. And here is a formula, very classical, known to Euler. And in weight 3, one can also do that. It's a little longer computation. But in weight 4, that's not longer true. So there are some multiple polylogarithms which cannot be reduced to Lie4, but Lie4 and Lie3(1) are always sufficient. And there is a statement which is a conjecture of Goncharov called depth conjecture, that a sum of multiple polylogarithms has depth d if and only if its des iterated truncated coproduct vanishes. So I'm not going to explain the meaning of the iterated truncated coproduct, but let me just say that if this conjecture is known, it will have lots of wonderful corollaries. So one of them would be a statement that volumes of hyperbolic polytopes can be, manifolds can be expressed via classical polylogarithms. That would follow. And also Zagier conjecture about special values of zeta functions would follow from the depth conjecture, more or less. There are some complications, but essentially, yes. And now these results are known up to dimension, up to n equal to 4. So in hyperbolic 7 space, volumes can be expressed through classical 4 logarithm, and there are these expressions for zeta functions at 3 and 4. But what is interesting about the depth conjecture is that if one takes polylogarithms of depths less greater or equal than half of the weight, then this criterion Goncharov gives is void. So for depths less than half of the weight, one should always be able to express polylogarithms through this depth. Sorry, I meant greater or equal than half of the weight. So what I mean is that one can show, and that's the result, that multiple polylogarithms of weight n can be expressed via polylogarithms of depth n over 2 or smaller. So that's the result. And I think it was known for weight 4 for a long time, and for weight 5 it was known, but I didn't know it's the result of Stephen Charlton. But already for n equal to 6, it certainly was new, and it was surprising because I tried to do it by elementary means for many years, and that was, I thought it's just wrong. So the proof of this conjecture is very, very close to the volume formula for order schemes and related to it. So one does the following: one takes a configuration of points on P1, and now one does the same thing, write down the same expression as in the volume formula for order schemes, except without square roots. So not taking square roots of cross ratios, just sum over quadrangulations, the same sum of polylogarithms over trees. And then one gets a function which I call quadrangular polylogarism. And the property of this function is that it has arbitrary weight depending on the sexto parameter m, and fixed depth, which is number of squares in this quadrangulation. And the simplest example is just for 4 points you get classical polylogarism of cross ratio, and for 6 points you get something more complicated but still manageable. And then one can show that actually this quadrangular polylogarithms are iterated integrals on P1, which means that basically they have a multi-valued loci where they have monodromy only on the boundary of the configuration space. And that's a surprising result, because each multiple polylogarithmic term is not like that. It has other divisors where it has complicated behavior. And using it, knowing that it's iterated integral on P1, one can relatively easily show using formality results that any iterated integral, and thus any arbitrary multiple polylogarism, can be expressed via this function. And this implies the Goncharov conjecture. So why these two functions are related, it's not clear to me at all. Let me say just one last thing and finish there. So these quadrangular polylogarithms are good for another reason. So one can write down equations they satisfy. And they satisfy a very simple equation, which we obtained with Andrei Matviakin. And basically, it's a simplest possible imaginable generalization of a 5-term relation, that you just take 5-term relation for dilogarism tells that you take 5 points and 5 cross ratios of them, and sum of dilogarisms vanishes. And here you take any number of points sufficiently big and take quadrangular polylogarism and sum them up, and you get 0. And if you use this equation, which is easy to show using iterated integrals, one gets 5-term relation by Abel for dilogarithm. One gets Goncharov equation and Kummer's equation for trilogarithm. And one gets the equation of Gangel and the results we used with Goncharov to prove Zagier's conjecture in weight 4 in higher depths, in depth 4. And in depth, in weight 6, we also used it to prove parts of depth conjecture. So this is will appear soon. And we, I mean, we conjecture, that's of course very naive, that all functional equations for multiple polylogarithms follow from this one. But I mean, we can just use it for now and see how helpful it is for proving the depth conjecture in general. Okay, thank you very much. And again, congratulations.
Thank you. Really interesting talk. Any questions or remarks or comments? Well, I have a standard question. In your isomorphisms between the moduli space of genus 0 with punctures and ortho schemes, using the structure we have mentioned several times, the stratification of modular space times the octant by descent d'enfant. Can this structure be transformed to the space of octa schemes times the octant? I mean, formally it can be transformed. Does it have any meaning?
So let me answer in the following way. So of course, the honest answer is I don't know, but there is a way to say this construction with order schemes in a very different way and in a very conceptual, maybe clear way. And it might happen that you will see from there whether it's true or not. So so the moduli space of points, configuration space, has a superstructure. There is a way to construct a super scheme of n points on P1. So basically, there will be more invariants, not just cross ratios. There will be some superversion of cross ratios, but also there will be Manin invariants of triples of points. And then one can look at the super scheme and the underlining manifold, the underlining usual scheme of the super scheme will be exactly this M0NS, which I mentioned, this where you add square roots of cross ratios, as far as I understand. And then it has a vector bundle. So then the idea is that on M0N, if you choose an ordering of points, cluster algebra machinery gives us a construction of a symplectic structure, which is kind of a Weil-Petersson form, a version of Weil-Petersson form. And then if you take this symplectic structure and extend it to superspace, but then restrict to the vector bundle, you will get that you have a vector bundle over M0N with quadratic structure, with a quadratic form. So I'm taking this vector bundle with this quadratic form, and I take their subbundles coming from forgetful morphisms. And this will give me order schemes living in the fibers of this bundle. So in a sense, it's a very natural construction. And for this one, just to see it, one just needs super scheme, and one needs a super symplectic structure related to Weil-Petersson. So, but I'm not sure whether that answers.
This is much better than nothing. Than just I don't know. Any other questions or remarks, please? Okay, then let's thank the speaker again. And now we close our session and almost close the conference, almost, because we have defined some times for concluding remarks. So perhaps we change to the mode where we see each other independently of where we are. So, hi, Sam. I didn't see you before. I start perhaps with the concluding remarks. Again, thank everybody very, very much for your congratulations and kind words addressed to me. Now, as a conclusion, I'd like to say maybe one general thing with a couple of mathematical examples that may be trivial, maybe no, for you to judge. So the topics of these conferences, you see, were quite diverse, and it is natural. Perhaps now I can share a small secret, the principle by which the people were invited to participate in this conference. The participants are my friends, colleagues, or people with whom we worked or shared our mathematical interests. Since mine are rather broad, thereafter we have this diversity. However, the maybe triviality that I was going to pronounce is that the mathematics is very unit. How I better say it, integral, an integral piece of our intellectual culture. And in particular, if some domains of mathematics seem quite unrelated to us now, it can happen that in some time they are going to be related. And I'd like to give a couple of examples just from this conference, and maybe closer to the main topic of activity of myself and my colleagues. And there was a funny thing when I heard Kolya Adrianov's talk, though we communicate and work together regularly. Only during this talk, I have realized that the combinatorics Kolya is interested in, that is the small corrections of totally regular passports, just spoiled in several places. So according to Kolya's recent works, we see that a very beautiful combinatorics is hidden besides that. But only today or yesterday, only yesterday, I realized that in the direction with which I am perhaps boring people for many years, I mean the passport certification of Horrid space. It just means that something interesting happens around the most singular points of the moduli space, to which these pairs with totally regular passports are. So I think this is another, this is just an example of the connection that we do not understand today, but I hope some progress in Kolya's research will make it closer. Something like that I would like to say about Anya Felikson's talk, which, as I said, I admired strongly, and almost every sentence, every formula was clear and understandable immediately. And I would say that the initial picture of Frieze is so beautiful that, of course, we'd like to see it related to anything well, to the descendant point theory understood in a broad enough way. Again, the first steps are made. Simple kinds of triangulations are covered by a very beautiful mathematics. May I express a hope that it is just a particular case of some beautiful relations. I think I could give more examples, even related only to the talks in this conference, but put a bit generally, I could say that we are starting to guess some relations between diverse parts of mathematics, continuing what Grothendieck understood in creating the Saint-Dapont theory. Our method is reliable but terribly slow. That means consider more and more cases until the general picture clarified. So, unfortunately, the life is short enough, and well, not all of us can hope to survive until the complete clarification. But what we can try to do is collect our results and hopes in such a way that those who is going to work after us will continue our efforts. So that's what I was going to say. Again, thanks to everybody. Now, any other people? Well. So, is it correct that there are no more concluding remarks? Well, maybe just somebody share the mathematical lens with the other participants. Well then, since nobody is obliged to say anything, many thanks again. Perhaps let's applaud to each other. So, and with the thanks to Yura, who made it possible, and generally to independent university on the base of which we work. Goodbye to everybody, with the hopes to meet in better times. So, bye.
Happy birthday.
Thank you,
George. Thank you, everybody. It's been a great mini conference. Thank you.
Так, Гриш, в любом случае, рад вас видеть, выздоравливайте, если вы уже не.
Добрый день, коллеги. Сори, я не пришел. Очно, но виртуальные есть.
Пару простых сюжетов про вычисление сумм при помощи картинок.
Давайте начнем с самого простого, что можно себе представить, а именно с вычисления суммы последовательных натуральных чисел. 1 плюс 2 плюс 3 и так далее плюс n. Но вот мне нравятся не компьютерные технологии, а наглядные демонстрации, поэтому сумму можно демонстрировать при помощи такого треугольничка сложного из квадратиков. Ну, точнее, в данном случае из кубиков. И чтобы вычислить сумму, можно взять два таких треугольника и сложить из них прямоугольник. Размеры этого прямоугольника n по высоте и n плюс 1 по ширине. И это так, получается такое известное вычисление суммы геометрической прогрессии. Но в этом случае, конечно, вот оно нарисовано. В этом случае, конечно, можно обойтись без всякой геометрии. И это, по сути, конечно, тоже рассуждение, что обычное с сложением, например, первого числа с прогрессией с последним, второго с предпоследним. На следующем примере уже обойтись без геометрии, чисто алгеброй тяжелее. Можно захотеть дальше вычислить не сумму первых степеней, а сумму квадратов. И как на это можно смотреть геометрически? Можно тоже составить такую пирамидку в самом верхнем уровне. 1 в квадрате кубиков, во втором 2 в квадрате, в третьем 3 в квадрате, ну и так далее, если нужно. Чтобы понять, что с такими пирамидками делать, ну, можно посмотреть на не на дискретную ситуацию в начале, а на непрерывную. Вот наше рассуждение для суммарифметической прогрессии – это было небольшое улучшение обычного рассуждения, которое доказывает формулу для площади треугольника, если угодно. Ну и у нее есть двумерный аналог. Можно, если рассмотреть сначала не пиксельную, а самую настоящую пирамиду, то можно заниматься тем, чтобы куб разрезать на несколько пирамид с квадратным основанием. Ну, это, в принципе, такая задача была на Московской математической олимпиаде лет 50 назад. И вот я нарисую вот такую картинку условную. Вот одна такая пирамида. А вот дальше на нас смотрит еще одна пирамида такая. Вот ее желтое основание. А справа третья пирамида. Если у вас плохо, как у меня, с пространственным воображением, и вы больше верите формулам, то можно написать и формулы, что одна пирамида соответствует тому, что самая большая координата z больше либо равно, чем x и y. Ну и две другие аналогично. Ясно, что из такого алгебраического описания особенно ясно, что мы действительно все порезали на три такие пирамиды, и что три такие пирамиды равны. Ну и можно считать, что такое рассуждение – это такое объяснение, как вычислять интеграл x степени n dx не определенный, да? От 0 до единицы, если угодно, от 0 до t. Как вычислять такой интеграл, не пользуясь формулой Ньютона-Лейбница, а так чисто геометрически. Ну ладно, нас интересует все-таки дискретная версия, но нужно попробовать взять три такие пирамидки и попробовать сложить из них куб или параллелепипед. Ну ни то, ни другое не получится, но получится нечто близкое. Вот можно взять и сложить вот такую штуку. Это уже почти то, что надо. Уж из двух таких фигур любой может сложить параллелепипед. И я хочу обратить внимание на 2,5 момента. Один момент такой, что алгебраически эту сумму посчитать можно, но не так просто. А с пирамидками разные школьники с энтузиазмом это складывают. Другой момент, что хотя алгебраическое решение есть, оно не получается из геометрического. Если в предыдущем случае мы просто так оформляли группировку членов, если угодно, сложение там чего-то с чем-то, то здесь, так как мы пирамидку поворачивали, на алгебраическом языке буквально такое рассуждение, видимо, не изложишь. Или, по крайней мере, я не знаю как. Ну и последний момент, что это начало длинной истории про то, как сумма связана с интегралом, что вот наша первая оценка была, что нужно было посмотреть на непрерывную задачу, она была проще. Ну и, а дальше после непрерывной задачи нужно как-то, вот все немножко не сходится, нужно как-то это исправлять. И это ведет к формулам Эйлера-Макларена и вот к этому всему, числам Бернулли и прочее. Но я про это, конечно, сейчас рассказывать не буду. У меня рассказ про детскую математику. Ну ладно, это совсем понятные вещи, что можно какие-то конечные суммы находить при помощи картинок. Менее очевидно, что можно на самом деле находить при помощи картинок и бесконечные суммы. Но самая простая бесконечная сумма — это, видимо, геометрическая прогрессия. У нас будет пока даже не произвольная геометрическая прогрессия, а вполне конкретная. Вот давайте квадрат разделим на 4 части, одну из них потом снова разделим на 4 части, и снова разделим на 4 части и так далее. Вот я смотрю теперь на закрашенную площадь. Ну, ясно, что эта закрашенная площадь, с одной стороны, это как раз сумма геометрической прогрессии. 1/4 плюс 1/16 плюс 1/64, да? Сумма 1/4 в степени n. А с другой стороны, если это был единичный квадрат. А с другой стороны, ясно, что эта площадь в точности равна 1/3. Ну, потому что, сами посудите, эта площадь такая же, как площадь под ней, и такая же, как площадь над ней. Действительно, вот розовых больших квадратов столько же желтых, и квадратов поменьше розовых столько же, сколько желтых, и еще поменьше столько же, сколько желтых. В общем, сейчас розовая, желтая и белая часть совершенно равновелики. Так что ответ 1/3. Такое тоже детское рассуждение. Рассуждение детское, но не очень понятно, как его обобщить, потому что если мы хотим что-нибудь более сложное считать, ну хотя бы 1/5 плюс 1/5 в квадрате плюс и так далее, то уже так не безумно понятно, что рисовать. Но способ на самом деле есть. Давайте снова посмотрим на квадрат и разделим его вот на внутренний квадратик и на такие трапеции. Причем так, что внутренний квадратик имеет площадь 1/5, что они все имеют одинаковую площадь. Но теперь понятно, что нам нужно сделать, если мы хотим взять 1/5. Вот нужно вот эту трапецию взять. И понятно, как процесс итерировать. Можно теперь взять во внутреннем квадратике, сделать совершенно то же самое и повторять все это. И ясно, что в конце концов мы закрасим ровно четверть квадрата. Поэтому эта сумма равна 1/4. И вообще так можно доказать, что вот такая сумма равна 1 делить на q минус 1. Ну, по крайней мере, если q целое. Ну, если вы верите там в что-то, в какое-то аналитическое продолжение, то этого достаточно. Ну, я давайте на всякий случай нарисую еще картинку для q равного не 5, а 6, например. Чтобы было понятно, что она для любого q работает. Ну вот, я взял, соответственно, пятиугольник. Внутри него рисую гомотетичный с тем же центром пятиугольник площади 1/6. Ну и вот будет наша сумма геометрической прогрессии. На самом деле так можно вычислять и более сложные суммы. Но вот я еще два примера покажу. Один из непосредственно развития предыдущего, что... Ну давайте покажу вот на примере такой картинки. можно начать с такой же картинки, но поступить с ней более сложно. Сначала давайте я закрашу не весь этот квадрат, а давайте я закрашу только вот такую букву Г. А на следующем шаге я возьму и закрашу две буквы Г поменьше. А еще на следующем шаге я закрашу три буквы Г, но еще меньше. Ну, ясно, что я все равно закрашу всю такую центральную треть. А какая сумма будет сразу не очень ясно, но ясно, что размер одной буквы Г уменьшается в геометрической прогрессии, а их количество постепенно растет. То есть это вычисление чего-то типа n делить на q в степени n. Ну, не буду сейчас объяснять, как эту сумму посчитать полностью, но только хочу сказать, что можно в таком же духе ну, такого рода суммы посчитать. Можно там более-менее любой многочлен вычислитель посчитать. Ну, это все, в принципе, известные вещи, но думаю, что здесь можно легко найти какие-то картинки, которые еще никто не придумал. Тут есть разные развития сюжета. Ну и даже вот я говорю, что вот такое можно для любого многочлена и любого целого q посчитать, но буквально такого я, конечно, не знаю только разные частные случаи интересные. Так что здесь можно... Есть простор для экспериментов. Но последнее все-таки, чтобы была не только совсем уж детские вещи, давайте я расскажу про какую-нибудь более интересную бесконечную сумму. Ну, интересные бесконечные суммы, наверное, начинаются с базельской задачи. То есть давайте посчитаем z-функция от 2, которая, то есть сумма обратных квадратов. Да? Как ни странно, здесь тоже можно порисовать картинки, и я не буду про это полностью объяснять, будет только короткий тизер. И он такого рода, что мы начнем снова вот с такой лесенки, как было в самом начале. Но только мы ее чуть-чуть продеформируем. Вот здесь нарисована продеформированная лесенка. Что в ней нарисовано? Вот эти длины, это... ну, вот здесь фигурируют квадраты чисел от вида 1 на n, поэтому не очень удивительно, что по осям мы отложим тоже числа вида единицы на n. Но мы это сделаем так несколько экзотично. Мы будем двигаться справа налево. То есть это 1, это 1 вторая, это 1 третья, это 1 четвертая. Я пока занимаюсь только конечной суммой. Вот. И мы вот разбиваем такой прямоугольник, такой большой квадрат на прямоугольнички и закрашиваем, ну, все на диагонали, а также все ниже нее. Получается такая деформированная лесенка. Кажется, наверное, правдоподобным, что это имеет какое-то отношение к этой сумме, но так сходу не скажешь, какое. Но вот, например, 1/4 в квадрате здесь легко найти, или 1/3 в квадрате здесь тоже легко найти. Но дальше уже не так ясно, но давайте будет спойлер, на самом деле, чтобы найти 1/2 в квадрате мы сложим из двух прямоугольничков. Вот они. Каждый имеет площадь 1/2 на 1/4, то есть в сумме у них как раз площадь 1/2 в квадрате. А оказывается, розовая площадь это как раз будет равна единице, хотя так совершенно сходу не очевидно. Но давайте я скажу такой общий спойлер, что значит, если отметить все прямоугольнички, у которых m и n взаимно просто, да, прямоугольнички 1 на m на 1 на n, у которых m и n взаимно просты, это будет такая сумма по взаимно... Давайте m и k лучше. По взаимно простым m и k 1 делить на mk. И еще у нас мы под диагональю. Это так как мы все перевернули, значит на самом деле, что m плюс k больше, чем n. И утверждается, что эта сумма всегда равна единице. Но если нот будет не 1, а какой-то t, то, соответственно, ясно, что эта сумма будет в t квадрат раз меньше, то есть 1 на t в квадрате. И у этого факта есть замечательное объяснение, которое связано с рядами Форрея. Если вы просто выпишете все дроби со знаменателем не больше n в порядке возрастания, несократимые, и посмотрите на равенности между соседними, то как раз они будут все иметь такой вид. И здесь написано просто, что если присуммировать все разности идти от нуля до единицы, то мы единицу и получим. Вот. Поэтому вот таким образом вся эта площадь, это на самом деле просто частичная сумма нашего ряда обратных квадратов. А чтобы посчитать этот ряд целиком, ну, нужно перейти к пределу. И если перейти к пределу, ну, уже видно, как это примерно выглядит. Здесь вырисовывается какая-то такая наклоненная кривая. На самом деле в пределе мы увидим вот такую штуку, которая задается уравнением на самом деле e в степени x плюс e в степени минус y больше либо равно единице. И, ну, конечно, если вы знаете такое утверждение, то вы легко докажете, что это сумма обратных квадратов. Да, нужно разложить логарифм в ряд, и все получится. Но и на самом деле эту площадь можно посчитать, воспользовавшись такой замечательной... Но это связано, на самом деле, с тропической геометрией. Да, это такая часть 1/3 амебы. И можно амебу превратить в треугольник. Можно, значит, посмотреть, все комплексифицировать и посмотреть на вот такое образование с двумя комплексными координатами и рассмотреть график этого образования в четырехмерном пространстве и посмотреть проекцию с вещественной части на чисто мнимую. Оно в силу голоморфности этих образований автоматически сохраняет площадь, и тогда амеба превратится в треугольник. И этот подсчет превратится в подсчет площади треугольника. И мы получим известное число π в квадрате на 6. Это, давайте, будет только спойлером, только таким обещанием какой-то математики. И уж в порядке совсем обещаний могу сказать, что зета-функция здесь появляется именно как, наверное, это было бы приятно, как объем пространства модулей, ну, эллиптических кривых в данном случае. И вот именно этот способ вычисления зета-функции куда-то обобщается. Можно таким же образом считать зета-функции типа вот такого, типа вот такой, которая тоже связана с объемом пространства модулей, но уже каким-то более сложным, каких-то же расслоений, кажется. Но я уже про это ничего не понимаю, поэтому на границе детской и взрослой математики останавливаюсь. Пусть дальше рассказывает кто-нибудь другой. Спасибо.
Да, спасибо. Так, тут хотелось бы понять, Даниил еще с нами. Так, я все-таки необходимое послесловие не могу не произнести. Это совсем побочный результат моей деятельности, ну да, в данном случае скорее моей. Значит, был такой человек Миньоли в каком-то там 1600 каком-то году, который на самом деле и от которого и идет задача о сумме обратных квадратов. А вообще он ученик этого самого Квальери и занимался строгим обоснованием всяких бесконечных сумм. Дальше идет моя фантазия, заключающаяся в том, что он, вот давайте ведем функцию Меньоля от какой-нибудь буквы Т, от x. Значит, фантазия заключается в том, что он не мог мне посчитать вот такую вот m от единицы. Это сколько там будет. Он, кстати, тоже какой-то геометрией при этом пользовался. Значит, это начинается с 1, 2 единица. Значит, m от 0, как мы знаем, это z от 2. Теперь всякий, пользуясь любым компьютерным устройством, может посчитать m от половинки, получить точный ответ, который мне еще удалось обосновать. m от 1/3 мне выдал какой-то замысловатый ответ, вот, который я могу понять, уже обосновать не могу. Потом, по-моему, ломается он на m от 1/5. Вот, и этим бы история, может, и закончилась, но я это обсуждал в своем курсе стекловки под зета-функциям, которым очень известным для меня образом заинтересовался Матиасевич. А вот Матиасевич подумал и прислал полный ответ. Поставил компьютерные эксперименты и функцию Меньоля полностью одолел. Вот такое послесловие. Значит, я думаю, что этот материал существует только в нашей переписке. Можно с ним что-то сделать.